You are listening to Azure Cosmos DB for developers, building scalable, globally distributed applications. Like and subscribe to keep up to date on our latest audiobooks. Azure Cosmos DB for developers, building scalable, globally distributed applications. Chapter 1, Welcome to the World of Azure Cosmos DB. 1.1 Introduction, the challenge of modern data, and the birth of Cosmos DB. In today's digital landscape, applications are no longer confined to local networks or single data centers. They serve users across continents, process vast streams of data, and demand instant responses, often from millions of concurrent individuals. From real-time gaming leaderboards and global retail platforms to sophisticated Internet of Things, IoT, solutions tracking countless devices, the underlying data infrastructure faces unprecedented challenges. Traditional relational databases, though robust for structured transactional workloads, often struggle to meet these new requirements for global distribution, elastic scalability, and guaranteed low latency at massive scale. This is where Azure Cosmos DB enters the picture. Conceived from Microsoft's internal need for a globally distributed, highly available, and performant database for its own large-scale services, Cosmos DB has a rich history. Its journey began as Project Florence and evolved into Azure Document DB, a pioneering NoSQL document database service. Learning from years of practical experience serving demanding applications worldwide, Microsoft re-architected and expanded Document DB into what we know today as Azure Cosmos DB. It represents a fundamental shift in how developers design and build applications that require data to be cloud-native, inherently distributed, infinitely scalable, and always on. As developers, our mission is to build applications that delight users, perform flawlessly, and scale effortlessly. Azure Cosmos DB provides the foundational database service that makes this mission achievable, enabling you to focus on your application's logic rather than the complexities of distributed database management. 1.2 Beyond traditional databases. Why NoSQL? For decades, relational databases, with their structured tables, rows, and SQL query language, have been the bedrock of enterprise applications. Their rigid schema and strong consistency guarantees are excellent for complex transactional workloads where data integrity is paramount. However, the rise of web-scale applications, mobile devices, and IoT necessitated new approaches to data storage and retrieval. This is the promise of NoSQL, or not only SQL, databases. They offer greater flexibility, horizontal scalability, and performance for specific data access patterns that traditional relational systems often struggle with. Instead of tables and rows, NoSQL databases often employ models like key-value pairs, wide columns, graphs, or, most commonly for many developers, documents. Document databases, which is where Azure Cosmos DB's native core, SQL API shines, store data in flexible, semi-structured formats like JSON. This flexibility means you don't need a predefined schema, allowing for rapid iteration and evolution of your data model as your application requirements change. More importantly, document databases are inherently designed for horizontal scaling, meaning they can distribute data across many servers to handle ever-increasing volumes of data and requests. This capability is crucial for applications that grow from hundreds to millions of users, eliminating bottlenecks that arise from vertical scaling limits of single servers. 1.3 Azure Cosmos DB, a global-scale solution for today's applications. At its core, Azure Cosmos DB is a fully managed, globally distributed, multi-model database service provided by Microsoft Azure. This fully managed aspect is key. It means Microsoft handles the infrastructure, patching, replication, and high availability, freeing developers from complex database administration tasks. One of its most compelling guarantees is its industry-leading service level agreements, or SLAs. For mission-critical applications that cannot afford downtime, Cosmos DB offers an impressive 5 nines, 99.999% availability for single-region accounts configured with strong consistency, and for multi-region accounts. This level of availability means your database is almost continuously accessible. capable of surviving entire region outages by seamlessly failing over to other configured regions. Imagine building a global e-commerce platform where users in London, New York, and Tokyo all access their shopping carts and product catalogs with consistently low latency, even if a data center halfway across the world experiences an issue. Cosmos DB is designed specifically for this kind of resilience and performance. 1.4 The foundational principles of Cosmos DB: availability, latency, scale, multi-model. Azure Cosmos DB is built upon 4 foundational principles, often referred to as its 4 pillars, that collectively deliver its unique capabilities. Global distribution with turnkey replication. Cosmos DB allows you to distribute your data across any number of Azure regions worldwide with the click of a button. This isn't just about disaster recovery. It's about placing data geographically closer to your users, ensuring low latency access regardless of where they are. Updates made in one region are automatically and transparently replicated to all other configured regions, ensuring high availability and global reach for your application. Elastic scalability of throughput and storage. You can independently scale throughput, the processing power for reads and writes, and storage for your database. As your application grows, you can provision more throughput or add storage as needed, elastically scaling up and down without application downtime. This means your database gracefully handles spikes in traffic, whether it's a sudden influx of players during a game launch or a holiday shopping rush. Guaranteed low latency. A hallmark of Cosmos DB is its promise of single-digit millisecond latency for both reads and writes at the 99th percentile, globally. This guarantee is critical for real-time applications where every millisecond counts, like interactive gaming, real-time analytics, or personalized content delivery. By placing data closest to your users, Cosmos DB minimizes network travel time, directly contributing to a snappier user experience. Multi-model and multi-API capabilities. While this book primarily focuses on the core SQL API, it's important to understand that Cosmos DB is inherently multi-model. This means it supports different ways of structuring and conceptualizing data, documents, key-value pairs, graphs, and wide-column stores, all powered by the same underlying, globally distributed engine. To accommodate these models, Cosmos DB offers various APIs that speak the language of common NoSQL databases, allowing developers familiar with those ecosystems to leverage Cosmos DB with minimal refactoring. 1.5 Understanding Request Units, RUs, your database budget and performance measure. When working with Azure Cosmos DB, you'll frequently encounter the term request units, or RUs. This is the fundamental currency for performance and cost in Cosmos DB. Instead of specifying CPU, memory, or IOPS, you provision throughput in terms of RUs per second, RUS. Every database operation, a read, a write, a query, or any other action, consumes a certain number of RUs. The RU cost of an operation depends on several factors. Item size. Larger documents consume more RUs for reads and writes. Index usage, whether an operation can be served by an index or requires a full scan, significantly impacts RU cost. Query complexity. Queries with filters, aggregations, ordering, or those spanning multiple partitions will naturally consume more RUs than simple point reads. Consistency level. Weaker consistency levels generally offer lower RU costs for read operations. Think of RUs as your database budget for performance. If you provision 1,000 RUs, your application can collectively perform operations that sum up to 1,000 RUs in any given second. If your operations exceed this provision throughput, Cosmos DB will throttle requests, returning a too many requests, error, HTTP 429 status code, indicating that you need to either provision more RUs or optimize your operations to consume fewer. Understanding and managing RUs is central to both optimizing your application's performance and controlling your Azure bill. 1.6 Key use cases and scenarios for developers across industries. Azure Cosmos DB's unique capabilities make it an ideal choice for a wide array of modern application scenarios. Internet of Things, IoT. Devices generate vast volumes of small, diverse data points at high velocity. Cosmos DB's ability to ingest and process millions of write operations per second, coupled with its flexible schema for varying device payloads, makes it perfect for IoT telemetry, connected car solutions, and smart home applications. Gaming. Online games require extremely low latency for player interactions, real-time leaderboards, and persistent player profiles. Cosmos DB's single-digit millisecond latency guarantees and global distribution capabilities ensure a fluid and responsive gaming experience for players around the world. Retail and e-commerce. Maintaining constantly updated product catalogs, managing customer orders, processing shopping carts, and serving personalized recommendations across a global customer base demands a database that scales transparently and delivers data quickly. For instance, a global e-commerce platform can leverage Cosmos DB to store product details. When a customer in Germany views a product, the data is served from a nearby Azure region, guaranteeing sub-10 millisecond latency. Simultaneously, the change feed instantly captures this browsing activity, triggering a real-time recommendation engine that leverages other linked Azure services to suggest complementary items, enhancing the customer experience without any perceivable delay. Web and mobile applications. Modern web and mobile apps often involve user profiles, activity feeds, chat functionalities, and real-time content delivery. Cosmos DB provides the backbone for these applications, offering high availability and low latency for user data, ensuring a smooth and engaging user experience. Real-time analytics. When combined with other Azure services like Azure Stream Analytics or Azure Functions, Cosmos DB can act as a high-throughput sink for streaming data, enabling real-time dashboards, anomaly detection, and immediate insights from diverse data sources. 1.7. A quick look at Cosmos DB's APIs, focusing on the core SQL API. As a multi-model database, Cosmos DB offers several APIs, each designed to make it easy for developers familiar with specific NoSQL paradigms to migrate or build new applications. Core SQL API. This is the native API for Cosmos DB. It stores data as schemaless JSON documents and allows you to query them using a SQL-like query language, which is incredibly powerful and flexible. This book will focus almost exclusively on the core SQL API, as it exposes Cosmos DB's native capabilities most directly and is often the API of choice for new applications. MongoDB API. For developers familiar with MongoDB, this API allows you to interact with Cosmos DB using MongoDB client drivers, treating Cosmos DB as a MongoDB server. Cassandra API. If you have applications built on Apache Cassandra, this API provides Cassandra-compatible access to Cosmos DB. Gremlin API. For graph database scenarios, the Gremlin API enables you to store and query highly connected data, e.g., social networks, recommendation engines, using the Apache Tinkerpop Gremlin traversal language. Table API provides a key-value store interface that is compatible with Azure Table Storage. While the diversity of APIs is a significant advantage for migration, the core SQL API is where Cosmos DB's unique features, performance guarantees, and efficiency truly shine. Mastering it equips you with the most direct and powerful way to build applications on this incredible platform. 1.8 Setting Expectations. What this book will empower you to do. Throughout this book, our goal is to transform you into a skilled Azure Cosmos DB developer. We will move beyond the theoretical to provide practical, actionable guidance that you can apply directly to your projects. By the end of this journey, you will be able to understand the fundamental concepts of NoSQL data modeling specifically for Cosmos DB, provision and configure Azure Cosmos DB accounts, databases, and containers, write efficient code using the Cosmos DB SDKs to perform CRUD operations and complex queries. Grasp the nuances of Cosmos DB's consistency models and select the right one for your application's needs. Master partitioning strategies to ensure your application scales gracefully and cost-effectively. Optimize performance and manage costs through effective indexing strategies and throughput provisioning. Leverage the change feed to build powerful event-driven and real-time solutions. Integrate Cosmos DB seamlessly with other vital Azure services to create holistic cloud applications. Implement best practices for monitoring, troubleshooting, and securing your Cosmos DB deployments. Let's embark on this journey to building scalable, globally distributed applications with Azure Cosmos DB. Chapter 2. Understanding NoSQL and Data Modeling for Cosmos DB. 2.1 From Relational to NoSQL. A paradigm shift in data management. For decades, the world of data was dominated by relational databases. Think of systems like SQL Server, MySQL, PostgreSQL, or Oracle. These databases are built on a highly structured model, where data is organized into tables with predefined schemas, rows, and columns. Relationships between tables are established using primary and foreign keys, and transactions adhere strictly to ACID properties, atomicity, consistency, isolation, durability, to ensure data integrity. The declarative SQL language made querying powerful and standardized. This relational model excels in scenarios requiring complex transactional consistency, like financial systems or rigid inventory management. However, as applications evolve to meet the demands of the Internet age, with its need for massive scale, flexibility, and global distribution, the traditional relational model began to show its limitations. Rigid schema. Changes to the schema, e.g., adding a new field to a table, can be complex and time-consuming, requiring downtime or careful migration, which is challenging for rapidly evolving applications. Vertical scaling. Relational databases often scale vertically by adding more power, CPU, RAM, faster disks, to a single server. This approach eventually hits limits and becomes expensive. Complex joins. While powerful, frequent, and complex joins across many tables can become a performance bottleneck at scale. This is where NoSQL, or not only SQL, databases stepped in. NoSQL databases embrace a fundamentally different philosophy. They trade some of the strict consistency guarantees and relational structure for flexible schema. Most NoSQL databases are schemaless or schema-on-read, meaning the structure of the data can evolve independently without requiring database-wide schema migrations. Horizontal scalability. NoSQL databases are designed to scale horizontally by distributing data across many servers, clusters, making it easier and often cheaper to handle petabytes of data and millions of requests per second. Optimized for specific data access patterns. Instead of a one-size-fits-all approach, different NoSQL models are optimized for different types of data and access patterns. There are several categories of NoSQL databases. Key-value stores. Simple, highly performant databases that store data as arbitrary key-value pairs, e.g., RIDIs. Column family stores. Store data in rows and dynamic columns, optimized for analytical queries over large datasets, e.g., Cassandra. Graph databases. Optimized for storing and querying highly connected data, representing entities and their relationships, e.g., Neo4j, Azure Cosmos DB Gremlin API. Document databases. Store data in self-contained, semi-structured documents, typically in JSON format. This model offers high flexibility and is excellent for rapid development and evolving data structures. This is the model Azure Cosmos DB's core, SQL, API primarily uses. For developers accustomed to the relational world, transitioning to NoSQL, especially the document model, requires a shift in thinking about data. It moves from focusing on how data is stored in normalized tables to focusing on how data is accessed and used by the application. 2.2 The Document Database Model. Flexibility, speed, and scale. Azure Cosmos DB, when using its core SQL API, operates as a document database. In this model, each piece of data, often representing an entity like a user, a product, or an order, is stored as a self-contained document. These documents are typically in JSON, JavaScript Object Notation format, which is a lightweight, human-readable data interchange format. A key characteristic of JSON documents is their flexibility. Unlike tables which enforce a rigid structure, JSON documents can contain varying fields, nested objects, and arrays. For example, one user document might have a shipping address field, while another might not, without requiring a change to the database's underlying structure. This schema-agnostic approach significantly accelerates development, especially when dealing with rapidly changing requirements or heterogeneous data. Example JSON document, user profile. ID, user 123. First name, Alice. Last name, Smith. Email, alicesmith@example.com. Address, Street, 123 Main Cent. City, Anytown. Zip code, 12,345. Preferences, email newsletter, product updates. Last login, 2023 to 10 to 26 T10 30Z. The self-contained nature of documents is also highly beneficial for performance. When an application needs details about a user, ideally, all relevant information is contained within that single user document. This means the database can retrieve everything in a single operation, potentially avoiding the need for multiple lookups or complex joins that would span across different tables in a relational system. This concept is fundamental to efficient data modeling in Cosmos DB. 2.3 Denormalization, the cornerstone of efficient NoSQL data modeling. In the relational world, a core principle is normalization. Normalization aims to reduce data redundancy by organizing data into separate tables and linking them with foreign keys. For instance, customer information and their orders would be in separate tables, linked by a customer ID. This minimizes data duplication, simplifies updates, you only update customer ID in one place, and helps maintain data integrity. However, in the NoSQL document world, particularly for distributed databases like Cosmos DB, the opposite principle often applies. Denormalization. You intentionally duplicate or embed data within documents to optimize query performance and reduce the number of read operations required. Why denormalize? Because joins, as you know them in SQL databases, don't exist in the same way in Cosmos DB. While you can perform some join-like operations using subqueries within the core SQL API, these are typically performed in memory and can incur significant request unit (RU) costs, especially across different data partitions. The most efficient operation in Cosmos DB is a point read, retrieving a single document by its ID and partition key. To maximize performance and minimize cost, your data model should enable your most frequent queries to be satisfied by as few document reads as possible. Scenario: imagine a blog application. In a relational database, you might have tables for posts, authors, and comments. Posts, post ID, title, content, authored. Authors, authored name, email. Comments, comment ID, post ID, user ID, comment text. To display a post with its author's name and all comments, you'd perform multiple joins in a document database. You might consider embedding the author's name and comment details directly within the post document. This denormalization means when you retrieve the post document, all the necessary information for display is immediately available in a single read operation, making it incredibly fast and cost-effective. 2.4 Embracing embedding. When to collocate data for performance. Embedding means nesting related data directly within a parent document. It's often the preferred approach in Cosmos DB for several reasons. Fewer round trips. All the data you need is retrieved in a single read operation, reducing network latency and RU consumption. Transactional consistency. Updates within a single document are atomic. If you modify a parent document and an embedded array within it, the entire operation is guaranteed to succeed or fail as a single unit. This is particularly useful for things like managing items in a shopping cart. Simpler application logic. Your application doesn't need to perform client-side joins or multiple database calls to assemble a complete view of an entity. When to embed, one-to-few relationships. When an entity has a few related items that are always accessed together. Example: a user document embedding their home and work addresses. Example from planning, shopping cart insight. A shopping cart document containing an array of line items. When a user views their cart, you want all items to load instantly. If this were normalized, you'd fetch the cart, Then iterate through the line item IDs and fetch each one. By embedding items, producted, quantity, name, price, directly in the cart document, it's a single, fast read. This also makes the add to cart or remove from cart operations atomic operations on a single document. Related data not frequently updated independently. If the embedded data is primarily read in the context of the parent and not often modified on its own. Bounded data size. There's an internal limit to the logical size of a document in Cosmos DB, currently 2 MB. Embedding works best when the embedded collection won't grow too large. If an entity could have hundreds or thousands of embedded items, it might exceed this limit or become cumbersome to manage. Example, product with embedded reviews, small number of reviews. id, prod 123. Name, super widget. Description, it widget super. Price, 49.99. Reviews, review it, rev 001. User id, user 999. Rating, 5. Comment, absolutely love it. Date, 2023 to 10 to 25. Review it, rev 002. User id, user 888. Rating, 4. Comment, good but wish the color was different. Date, 2023 to 10 to 26. 2.5 Referencing documents. When to link data and manage relationships. While embedding is often preferred for performance, there are scenarios where referencing is necessary. Referencing means storing the ID of a related document within another document, similar to how foreign keys work in relational databases. You then rely on your application logic, or occasionally Cosmos DB subqueries to fetch the related document. When to reference? Many-to-many relationships, for example, products and categories. A product can be in multiple categories, and a category can have many products. One-to-many with unbounded growth, when related data might grow very large, exceeding the 2 MB document limit. Example from planning, social media with many comments. If a blog post could have thousands of comments, embedding them all directly into the post document would eventually exceed the 2 MB limit. In this case, storing commenteds, references, within the post and fetching comments separately is more appropriate. Or, even better, creating comment documents linked by a post ID. Frequently updated, shared data. If a piece of data is shared across many parent documents and is frequently updated, embedding it everywhere would lead to severe data inconsistency issues and costly updates across many documents. Example, a category document containing category name, which is referenced by many product documents. If category name changes, you only update it in one category document, not millions of products. Data accessed independently, if the related data is often accessed without its parent. Example, users and their roles. Roles are often updated independently and accessed without needing all the user's details. Example, product referencing category. Product category document. id, CAD electronics. Name, electronics. Product document, references category. id, prod 456. Name, smartwatch. Description, wearable tech for health and notifications. Price, $299.99. Category id, CAD electronics, reference. To get the product details along with the category name, your application would first fetch prod 456. Then take category id, CAD electronics, and perform a second read to fetch the CAD electronics document. 2.6 Modeling relationships in Cosmos DB. Thinking beyond traditional joins. Since explicit joins are not a native performant feature in Cosmos DB's core, SQL API, you must rethink how relationships are managed. Your data modeling design should prioritize the queries your application performs most frequently. Here are common patterns for handling relationships. Denormalization, embedding. As discussed, this is the most performant for tightly coupled one-to-few data. Social media example, embedding comments. For a blog or small-scale social media, if comments are not too numerous and are primarily viewed with the post, embedding them directly into the post document is efficient. Post document with embedded comments. id, post 123. Title, my first blog post. Content, authored, user app. Comments, a commented. C001, userid, userx's text, great post. Commented, C002, userid, userker text, very insightful. This is fast to retrieve the post and its comments, but updating a single comment involves updating the whole post document and querying comments independently, e.g., all comments by userxes would be inefficient. Referencing application-side joins for one-to-many with potentially unbounded growth or many-to-many relationships. The application performs multiple GET operations. Social media example, referencing comments. If a post can have hundreds or thousands of comments, store comments as separate documents, each referencing the post ID. Post document. Id, post 123. Title, my first blog post. Content, authored, userabc. Separate comment documents. Id, C001, posted. Post 123, userid. Userxes text, great post. Id, C002, posted. Post 123, userid. Userpker text, very insightful. To get all comments for a post, you'd execute a query like select from C, where C posted equals post 123. This query performs well if posted is part of your partition key or is indexed. Your application then stitches the data together. Duplicating data, denormalization for reads. If a piece of data is frequently needed alongside another entity, but doesn't change often, you might duplicate it. Social media example, denormalizing author name. To avoid fetching the author document every time a post is displayed, you could embed the author name directly in the post document. Post document with denormalized author name. Id, post 123. Title, my first blog post. Content, authored, userabc. Author name, John Doe, denormalized date. The trade-off here is that if John Doe changes their name, you would need to update every post document containing that denormalized author name. This is where you need to weigh the cost of updating many documents versus the cost of frequent lookups. Usually, for data that changes rarely or for lookup that is critical for performance, denormalization is preferred. For data that changes often, then you should only reference it. The key is to ask, how will I query this data most often? Design your documents to make those most frequent queries as simple and efficient as possible, even if it means some data duplication. 2.7 Hybrid models and common anti-patterns to avoid. Most complex applications will employ a hybrid approach, mixing embedding and referencing as appropriate for different entities and relationships. The goal is always to strike the optimal balance between read performance, write performance, storage cost, and consistency. Common anti-patterns to avoid: over-normalizing, treating Cosmos DB like a relational database and creating many small, linked documents. This leads to excessive multi-document queries, client-side joins, and high RU costs. Over-embedding, embedding too much data without considering document size limits, 2 MB logical, or the frequency of independent updates. This can lead to very large documents that are expensive to read and write, or consistency issues if duplicated data needs to be simultaneously updated across many documents. Using join in queries extensively. While Cosmos DB's SQL API supports joins on subqueries and join within stored procedures, they are not designed for large-scale, complex relational joins. Misusing them for this purpose will lead to poor performance and high RU consumption. Ignoring read patterns. Designing the model without a clear understanding of the most frequent queries means you'll likely incur high costs for basic operations. Always prioritize your read access patterns. Lack of versioning change management. As schemas are flexible, changes to document structure must be handled carefully in your application code. Your application needs to be resilient to encountering older versions of documents, e.g., a field might be missing in an older document. 2.8 The iterative nature of NoSQL data modeling. Design, test, refine. Unlike relational database design, which often involves a detailed upfront schema definition, NoSQL data modeling is inherently more iterative and evolutionary. Start with the core entities and most frequent queries. Begin by identifying your main entities, e.g., users, products, orders, and crucially, how your application will read them most often. Sketch initial document structures. Based on your primary query patterns, sketch out how these entities might look as JSON documents, considering embedding versus referencing. Prototyping and testing. Implement a small prototype. Use the Azure Cosmos DB emulator for local development or a small provisioned container in Azure. Load sample data. Execute your critical queries and monitor their request unit, RU, consumption, and latency. This practical testing is invaluable. Analyze and refine. Are queries performing as expected? Are RUs too high? Is data growth manageable? Are there conflicts? Based on this feedback, refine your data model. You might decide to embed more data, denormalize a field, or change how a relationship is managed. Scaling and monitoring. As your application scales, continue to monitor performance and RU consumption. Hot partitions, which we'll discuss in a later chapter, might indicate an issue with your chosen partition key, which is itself entwined with your data model. This iterative process means your Cosmos DB data model might evolve over time, adapting to changing business needs and performance insights. The flexibility of the document model makes this evolution considerably easier than in a rigid relational environment. By embracing this approach, you'll develop a data model that not only performs incredibly well today, but can also adapt to the demands of tomorrow. Chapter 3, Getting Started. Your first Cosmos DB account and database. 3.1, Provisioning your Cosmos DB account in the Azure portal. A guided tour. Before you can start building applications with Azure Cosmos DB, you need a place to store your data. This begins with creating an Azure Cosmos DB account, which serves as the top-level unit of your database infrastructure. It's essentially the entry point to your databases and containers. Let's walk through the process of creating your first Cosmos DB account using the Azure portal. Log in to the Azure portal, open your web browser, and navigate to portal.azure.com. Log in with your Azure account credentials. Search for Azure Cosmos DB. In the search bar at the top of the portal, type Azure Cosmos DB and select Azure Cosmos DB from the search results. Create a new account. On the Azure Cosmos DB page, click the +Create button. This will take you to the Create Azure Cosmos DB Account wizard. Now, you'll see a series of tabs where you configure your account. Let's focus on the Basics tab first. Subscription. Choose the Azure subscription you want to use. This is where your costs will be billed. Resource Group. A resource group is a logical container for Azure resources. You can create a new one for your Cosmos DB account, e.g., mycosmos DBRG, or select an existing one. Using a dedicated resource group helps organize and manage your resources, especially when you need to delete them later. Account name. This must be a globally unique name, lowercase, with no spaces. This name will become part of your Cosmos DB endpoint URL, e.g., https://youraccountname.documents.azure.com. Choose something descriptive like My First Cosmos DB or Dev eCommerce DB. Location. Select the Azure region where you want your primary Cosmos DB account to reside. This is a critical choice for production applications, as it impacts latency for users closest to that region and also affects data residency requirements. For development, pick a region close to you. Capacity mode. This is a crucial setting that dictates how you provision and pay for throughput. You have two main options: provisioned throughput and serverless. For now, you can leave the default as provisioned throughput, but we'll discuss these in more detail in section 3.4. Free tier discount. If available, you'll see an option to enable the free tier discount. This is excellent for development and testing, providing 1,000 RUS and 25 GB of storage free each month. Enable this if you're experimenting. Limit total account throughput. For provisioned throughput accounts, you can optionally set a limit on the total throughput, RUS, for the entire account. This helps control costs. For your first account, leaving it unchecked is fine. Apply free tier discount. If you qualify for and wish to use the free tier, ensure this box is checked. You can then click Review + Create to use default settings for the other tabs, network, backup policy, encryption tags. For a simple Getting Started account, the defaults are usually sufficient. For production, you would explore these tabs more deeply to configure network security, VNet integration, firewalls, backup mechanisms, and encryption settings. Finally, on the Review plus Create tab, review your settings and click Create. Deployment usually takes a few minutes. 3.2 Navigating the Cosmos DB Blade. An overview of key developer features. Once your Azure Cosmos DB account deployment is complete, navigate to the resource in the Azure portal. You'll land on the Overview page, often called the Blade in Azure terminology. This page provides a summary of your account's health, key metrics, and quick access to important features. On the left-hand navigation pane, you'll see several sections. As a developer, the most frequently used sections will be Data Explorer. This is your web-based playground for interacting directly with your Cosmos DB data. You can create databases and containers, edit documents, and execute queries right from your browser. We'll delve into this in section 3.6. Keys. This section provides the connection strings and access keys required for your applications to connect to your Cosmos DB account. This is vital for programmatic access. We'll cover this in section 3.7. Replicate data globally. If you want to enable global distribution for your account, this is where you add additional Azure regions for replication. Scale and settings. Here you can adjust your account-level throughput, RUS, and other settings. Monitoring provides access to Azure Monitor metrics and diagnostic logs, which are crucial for understanding your database's performance and troubleshooting issues. For the purpose of getting started, the Data Explorer and Keys sections will be your primary focus. 3.3 Choosing your API. Focusing on the core SQL API for development. During the account creation process, you had the option to choose an API. While Azure Cosmos DB is a multi-model database supporting several APIs core, SQL, MongoDB, Cassandra, Gremlin, Table, this book focuses almost exclusively on the core SQL API. The core SQL API is the native API for Azure Cosmos DB. This means it fully leverages all of Cosmos DB's unique features and performance guarantees, and it generally provides the most direct control over the database's capabilities. It stores data as JSON documents, and you interact with it using a powerful, SQL-like query language, hence the SQL in its name. For new applications built from scratch on Cosmos DB, the core SQL API is often the recommended choice. If you're coming from a MongoDB background, the MongoDB API might feel more familiar. And for migrating existing Cassandra or Gremlin applications, those APIs are valuable. However, for a deep dive into Cosmos DB's core strengths, the core SQL API is your best starting point. All examples and concepts in the coming chapters will assume you are using the core SQL API. 3.4 Understanding capacity modes. Provisioned throughput versus serverless for cost and scale. One of the most important decisions when setting up Cosmos DB is your capacity mode, which directly impacts how you pay and how your database scales. Provisioned throughput. This is the traditional model where you explicitly specify the amount of throughput in request units per second, RUS, that you expect your application to need. Manual throughput. You set a fixed number of RUS, e.g., 400 RUS, 10,000 RUS. You pay for this capacity hourly, whether you use it or not. This is ideal for applications with very predictable and consistent workloads. If your consumption exceeds the provisioned RUS, subsequent requests will be throttled. You'll get HTTP 429 too many requests errors, until more RUs become available. Autoscale throughput, recommended for variable loads. With autoscale, you specify a maximum RUS, e.g., 4,000 RUS. Cosmos DB will then automatically scale the actual provision throughput between 10% of that maximum and the maximum. For example, if you set a max of 4,000 RUS, it will scale between 400 RUS and 4,000 RUS, based on your current workload. You only pay for the highest RUS used within that hour, but never more than your configured maximum. This is excellent for applications with variable or unpredictable traffic patterns, as it prevents throttling while optimizing costs. You can provision throughput at two levels. Database level. All containers within that database share the total provisioned RUS This can be cost-effective for applications with many containers where individual container workloads fluctuate, but the aggregate load is predictable. Container level. Each container has its own dedicated provisioned RU. This offers isolated performance guarantees for specific containers, essential for mission-critical data stores. Serverless. This is a consumption-based model. Instead of pre-provisioning throughput, you pay only for the request units your database operations actually consume and for the storage you use. Pay-per-request. There are no minimum RUs to provision, and thus no minimum hourly costs for throughput. Ideal for sporadic workloads. Perfect for development environments, test accounts, applications with intermittent traffic, e.g., batch processing, internal tools, or those with highly unpredictable usage where you don't want to manage scaling. No throughput guarantee. While convenient, serverless doesn't offer the same low-latency guarantees as provisioned throughput. It's generally not recommended for high-performance, consistent production workloads that require predictable, low-latency responses. For getting started, serverless is often a great choice as it has no minimum cost and allows you to experiment without worrying about provisioned RU bills. For a production application, auto-scale throughput at the container level is a common and robust choice, balancing performance with cost efficiency for variable loads. 3.5. Creating databases and containers. Structuring your data's home. With your Cosmos DB account provisioned, the next step is to create databases and containers to store your data. Think of it like this. Cosmos DB account, your entire Cosmos DB service instance in Azure. Database, a logical grouping for your containers. You can have multiple databases within an account. Container. This is where your actual data documents, items resides. It's the unit of scalability for both throughput and storage. In the core SQL API, containers hold JSON documents. In other APIs, they might hold collections, MongoDB, tables, Table API, or graphs, Gremlin. Let's create your first database and container using the Data Explorer. Open Data Explorer. In your Cosmos DB account blade in the Azure portal, click Data Explorer from the left-hand menu. Create New Container. Click the New Container button. It looks like a plus sign with a database icon next to it. A new container panel will slide out. Here are the key fields to configure. Database ID. Enter a unique name for your database, e.g., My App Data. You'll also see an option to provision database throughput. If you check this, all containers within this database will share the RUs set at the database level. If left unchecked, you will provision throughput at the container level, which is our recommendation for most production scenarios as it gives more granular control. Container ID. Enter a unique name for your container, e.g., users or products. This is where your documents will be stored. Partition key. This is arguably the most critical design decision in Cosmos DB and cannot be changed after creation. The partition key determines how your data is distributed across logical partitions. Choosing the right partition key is fundamental to achieving high performance and scalability. For example, if you often query user data by userid, then userid would be a good candidate for your partition key. Always precede the key with a /, e.g., my property name. While you can start with a simple key like id for initial development, it's crucial to understand that for production, you must choose a partition key that evenly distributes both data and request volume. A poor choice can lead to hot partitions and negatively impact performance and cost. We will dive deep into partition keys in Chapter 8. Throughput, auto-scale, or manual. If you didn't provision throughput at the database level, you'll configure it here for this specific container. Select either auto-scale, recommended for most, or manual, and set your RUs. Click OK to create your database and container. Once created, you'll see your database and container listed in the Data Explorer on the left, ready to store documents. 3.6. The power of the Data Explorer. Your in-portal development tool. The Data Explorer within the Azure portal is an incredibly useful tool for developers, especially during the initial stages of development and for quick debugging. It's a web-based interface that allows you to interact with your Cosmos DB resources without writing any code. Here's what you can do with the Data Explorer. Browse items. Select a container, then click Items. You'll see a list of documents in that container. You can click on individual items to view and edit their JSON content. You can also create new items directly. Run queries. Select a container, then click New SQL Query. A query editor will open where you can write and execute SQL-like queries against your documents. This is excellent for testing your data model and understanding query results. After running a query, you'll see the results and, crucially, the request units, RUs consumed by that query, giving you immediate feedback on its cost. Create server-side logic. You can also create new stored procedures, triggers, and user-defined functions, UDFs, directly in JavaScript by clicking New Stored Procedure, New UDF, or New Trigger. These are powerful for server-side logic and transactions. Manage scale. Rapidly change the throughput for a container or database. Upload/download data. Easily import and export data for testing. The Data Explorer serves as a convenient sandbox that enables you to quickly prototype, test, and debug your data model and queries directly in the cloud. It's a great companion when learning and developing. 3.7. Connecting your application. Securely using connection strings and keys. Once your Cosmos DB account and container are set up, your application needs a way to connect to it. This is done using connection strings and access keys. Accessing keys. In your Cosmos DB account blade in the Azure portal, click on Keys in the left-hand menu. Understanding the keys, you'll see several keys and connection strings, URI. This is your Cosmos DB endpoint URL, e.g., https youraccountname.documents.azure.com:443/. Primary key/secondary key. These are your master access keys. They grant full read-write access to all databases and containers within your account. You typically use the primary key. The secondary key is available for key rotation, allowing you to cycle keys without downtime. Read-only keys. These keys provide read-only access, useful for applications that only need to retrieve data. Primary-secondary connection, string. These combine the URI and the primary-secondary key into a single string. It's usually the easiest way to connect your application initially. Connecting with the SDK. When you use one of the Azure Cosmos DB SDKs, for .NET, Java, Node.js, Python, etc., you'll typically initialize your Cosmos client object using the primary connection string or the URI and primary key separately. Example, conceptual actual SDK syntax varies. Initialize Cosmos DB client. Cosmos client equals new Cosmos client, your Cosmos DB connection string. Security warning. Never hardcode connections, strings, or keys directly into your application's source code. This is a major security risk. If your code repository is compromised, your database could be exposed. Instead, follow these secure practices. Environment variables. Store connection strings as environment variables on your application's host, e.g., Azure App Service, Azure Functions. Azure Key Vault, the most secure method for production applications. Azure Key Vault is a service that securely stores and manages cryptographic keys and secrets. Your application can retrieve the connection string from Key Vault at runtime. Managed identities. For Azure-hosted applications, like Azure Functions, App Services, VMS, managed identities provide an identity for your service that can be granted access to other Azure resources, like Cosmos DB, without needing to store credentials. This is the most secure and recommended approach for cloud-native applications. For initial development and testing, using an environment variable is often the simplest step up from hardcoding. 3.8. Developing locally with the Azure Cosmos DB emulator, a sandbox for your code. While connecting to a cloud-based Cosmos DB account is essential, constantly hitting the cloud for every development and testing iteration can consume RUs and incur costs. This is where the Azure Cosmos DB emulator comes in. The emulator is a local, high-fidelity environment that emulates the Azure Cosmos DB service on your development machine. It's designed to mimic the cloud service as closely as possible, allowing you to develop and test your applications without an internet connection or incurring any Azure costs. How to get started with the emulator? Download and install. The emulator is a free download available from the Microsoft documentation. Simply search for Azure Cosmos DB emulator online. Start the emulator. Once installed, you'll typically find it in your Start menu. Launching, it will start a local Cosmos DB instance, usually accessible via a browser icon in your system tray. Local connection details. The emulator provides its own default connection string and keys that you can use in your application. These usually point to HTTPS localhost :8081. You can retrieve these from the emulator's UI. Data Explorer integration. The emulator often comes with its own local Data Explorer accessible via your browser, mirroring the functionality in the Azure portal. Benefits of using the emulator: cost-free development, no Azure consumption charges, offline productivity, develop and test your application even without an internet connection, rapid iteration, faster debugging and testing cycles as you're interacting with a local service. Limitations of the emulator: performance differences. While functional, the emulator is not designed for high performance or stress testing. Its performance characteristics will not match a scaled-out cloud deployment. Feature parity. While generally very close, new Cosmos DB features in the cloud might not be immediately available in the emulator version. Global distribution. The emulator cannot simulate global distribution or multi-region write scenarios. The emulator is an invaluable tool for your daily development workflow, acting as a reliable sandbox for prototyping and testing your data models and application logic before deploying to a cloud-based Cosmos DB account. Many developers use a workflow where they start locally with the emulator, then deploy to a low-cost cloud account, e.g., serverless or free tier for integration testing, and finally to a production-configured account for full-scale operations. 3.9 Initial Setup Best Practices, setting the stage for success. As you embark on your Azure Cosmos DB journey, keep these initial best practices in mind. Start small and iterative. Begin with a serverless account or a low RUS provisioned account. The Cosmos DB emulator is your best friend for early development, allowing you to iterate rapidly without cost. Think about your partition key early. We'll dedicate an entire chapter to this, but it's crucial to understand now that your partition key choice impacts scalability and performance significantly and cannot be changed later without data migration. Even for initial development, try to use a representative partition key based on your planned query patterns, e.g., customer id, product id. Secure your connection details. Never hardcode connection strings. Use environment variables for dev/test and graduate to Azure Key Vault or managed identities for production. Monitor RU consumption. As soon as you start running queries or operations, check the RU cost in the Data Explorer or programmatically via the SDKs response. This gives you early feedback on the efficiency of your operations. Choose regions carefully. For production, consider placing your Cosmos DB account and replica regions geographically close to your user base to minimize latency. Factor in data residency requirements. By following these guidelines, you'll establish a solid foundation for building efficient, scalable, and secure applications with Azure Cosmos DB. You're now ready to move beyond setup and start interacting with your data. Chapter 4. The Cosmos DB SDKs, your development toolkit. 4.1 Introduction to Cosmos DB SDKs. The bridge between your application and your data. Having set up your Azure Cosmos DB account and created your first database and container, the next crucial step is to enable your application to interact with this powerful service. While the Azure Portal's Data Explorer is excellent for quick tests and browsing, real-world applications require programmatic access. This is where the Azure Cosmos DB software development kits, SDKs, come in. An SDK is a collection of tools, libraries, and documentation that developers use to create applications for a specific platform. For Azure Cosmos DB, the SDKs provide a well-defined, idiomatic way for applications written in various popular programming languages to connect to, manage, and perform operations on your Cosmos DB data. Microsoft provides official SDKs for major languages and platforms, including .NET C#, Java, Node.js, JavaScript, TypeScript, Python, These SDKs act as the essential bridge between your application logic and your globally distributed Cosmos DB database. They handle the underlying complexities of network communication, authentication, serialization, and deserialization of JSON data, allowing you to focus on your application's business requirements. 4.2 Across SDK perspective, common object models and programming patterns. While the specific syntax and naming conventions may vary slightly across different programming languages, the core object model and programming patterns within the Azure Cosmos DB SDKs are remarkably consistent. This means that once you understand how to perform an operation in one SDK, you'll find it conceptually similar to perform the same operation in another. Every SDK typically exposes core objects representing the hierarchical structure of your Cosmos DB resources. Cosmos Client. This is the top-level object representing your connection to the Azure Cosmos DB service. It's the gateway for all operations. Database Object. From the client, you can obtain a reference to a specific database within your Cosmos DB account. This object represents the logical container for your data collections. Container Object. From the database object, you can get a reference to a specific container, also sometimes referred to as a collection. This is where your individual items, documents, reside. Item Objects. These represent the actual JSON documents stored within your containers. The SDKs provide methods to create, read, update, and delete these items. Beyond these fundamental structural objects, you'll find common methods for creating, reading, updating, and deleting CRUD items, essential operations to manage your data. Querying data, executing SQL-like queries against your containers. Batch operations, performing multiple operations within a single transaction. Response handling, retrieving the results of operations, including metadata like request unit charges. Error handling, managing exceptions and transient failures. Understanding these common abstractions will make your learning process smoother, regardless of which language you primarily use. 4.3 Initializing your Cosmos client. The gateway to your database. The first step in any application that uses Cosmos DB is to initialize an instance of the Cosmos client, or its language-specific equivalent like Cosmos client in Java or Cosmos client in Node.js. This client object is responsible for managing connections to the Cosmos DB service. When you initialize the client, you typically provide your Cosmos DB endpoint URL and your master key, or a more secure credential provider if using managed identities or Azure Active Directory. Practical tip: the singleton pattern for client initialization. For most applications, particularly server-side applications that handle many concurrent requests, like web APIs or microservices, it is a critical best practice to use a single instance of the Cosmos client object throughout the lifetime of your application. This is commonly referred to as the singleton pattern. Why is this so important? The Cosmos client object is designed to be thread-safe and efficient across multiple concurrent operations. Internally, it manages a pool of TCP connections to Cosmos DB. Creating a new Cosmos client instance for every request to your database is highly inefficient. Increased latency. Each new client initialization incurs overhead for setting up connections, leading to higher latency for every operation. Resource exhaustion. Repeatedly opening and closing TCP connections can exhaust network resources and port limits on your application server, potentially leading to connection errors and instability. Higher resource consumption. Managing multiple active client instances consumes more memory and CPU on your application server. By creating a single Cosmos client instance at application startup and reusing it across all requests, you significantly reduce overhead, minimize latency, and improve the overall efficiency and stability of your application. This persistent client allows for connection pooling and proper resource management, making it the most performant and reliable approach. 4.4 Programmatically working with databases and containers. Once you have an initialized Cosmos client instance, you can use it to interact with your Cosmos DB account at higher levels before diving into item operations. The SDKs provide methods to create a database. If your database doesn't exist, you can programmatically create it. You'll specify a database ID and optionally set throughput for the database, if using database-level throughput. Get a database reference. If the database already exists, you can obtain a reference to it using its ID. This allows you to then work with containers within that database. Create a container. Within a database, you can create new containers. When creating a container, you must provide a container ID and, crucially, define its partition key path. As discussed in Chapter 3, the partition key is fundamental to how Cosmos DB shards your data, and its correct selection is vital for performance and scalability. You'll also specify the throughput for the container if using container-level throughput. Get a container reference. Once a container is created, you can get a reference to it, which is the object you'll primarily use to perform CRUD operations and queries on your documents. Delete databases or containers. For cleanup or specific application logic, the SDKs also provide methods to delete databases or containers. These programmatic management capabilities are essential for automated deployments, data migration scripts, or applications that dynamically provision or manage their data stores. 4.5. Understanding response objects and HTTP status codes. What your database is telling you. Every operation you perform using the Cosmos DB SDKs, whether it's creating an item, reading one, sending a query, or deleting a document, will return a response object. This response object is much more than just the data you requested. It contains critical metadata about the operation itself. Key information typically found in a Cosmos DB response object includes HTTP status code. This indicates the outcome of the operation. Familiarize yourself with common HTTP status codes like 200 OK, the request was successful. 201 created. A new resource was created successfully. 204 no content. The request was successful, but there's no content to return, e.g. successful deletion. 400 bad request. The request was malformed or invalid. 401 unauthorized. Authentication failed. 403 forbidden. The authenticated user does not have permission. 404 not found. The requested resource item, database, container does not exist. 409 conflict. An item with the same ID and partition key already exists, e.g., when trying to create a duplicate. 429 too many requests. This is a crucial one. It means you have exceeded your provisioned request units. Cosmos DB is throttling your requests. 500 internal server error. An unexpected error occurred on the server side. Request units, RUs, consumed. This is vital for cost management and performance tuning. The response object will include a property, e.g., request charge, activity id, indicating the number of RUs consumed by that specific operation. Regularly checking this allows you to identify and optimize expensive queries or operations. eTag, entity tag. For read and write operations, the eTag signifies the specific version of the resource. eTags are crucial for optimistic concurrency control, which we'll discuss in Chapter 5. Latency. Some SDKs provide information on the latency of the operation, e.g., how long the request took round trip. This helps diagnose performance issues. Item or feed data. For successful operations, the actual data, the item you read, or the list of items from a query will be present. Always inspect the response objects, especially during development, to understand the behavior and cost implications of your Cosmos DB operations. 4.6 Error handling, timeouts, and leveraging automatic retries. Building robust applications means handling errors gracefully. In a distributed system like Cosmos DB, transient network issues, temporary service unavailability, or even hitting your provisioned throughput limits, 429 errors are normal occurrences. The Cosmos DB SDKs are designed with these realities in mind. Each SDK provides mechanisms for error handling, typically through exceptions in languages like Net or Java, or error-first callbacks promises in Node.js. When an operation fails, the SDK will throw an exception or return an error object containing details about what went wrong, including the HTTP status code. A critical feature built into the Cosmos DB SDKs is automatic retry logic. When certain transient HTTP status codes are returned by the service, like 429, too many requests, or 503, service unavailable, the SDK will automatically pause and retry the operation a configurable number of times. This significantly enhances the resilience of your application, making it tolerant to momentary service issues or temporary throttling. Anecdote: the silent hero of resilience. Consider a large production e-commerce application that experiences a sudden but brief increase in traffic, perhaps due to a flash sale. The application might temporarily exceed its provisioned request units, leading to some 429 errors from Cosmos DB. Without proper retry logic, these user requests might immediately fail, leading to frustrated customers and lost sales. However, because the development team correctly leveraged the Cosmos DB SDK with its default retry policies, these initial 429 responses were silently handled by the SDK. The SDK automatically paused for a few milliseconds, retried the operation, and often succeeded on the second or third attempt as the service caught up. From the end user's perspective, the operation simply took a tiny bit longer, but it completed successfully. The transparent retry mechanism of the SDK became a silent hero, preventing service disruption and ensuring a smooth customer experience during a peak load. While the default retry policies are often sufficient, you can usually configure them within the SDK client options to fine-tune aspects like the maximum number of retries or the total timeout duration for an operation. For persistent, non-transient errors, like 400 bad request or 404 not found, the SDK will not retry, as these indicate a problem with the request itself rather than a temporary service issue. Your application code should then handle these specific errors. 4.7 Configuring connection options, optimizing performance and network behavior. Beyond the core connection string, the Cosmos client constructor, or its equivalent configuration object, typically allows you to specify various connection options that can significantly impact your application's performance and behavior. These include connection mode, direct mode recommended. The SDK connects directly to the backend Cosmos DB replicas using TCP. This mode offers the best performance in terms of latency and throughput and is generally the recommended choice for most workloads. Gateway mode, HTTPS. The SDK connects to Cosmos DB through a front-end gateway service using HTTPS. This mode is useful in restricted network environments where direct TCP access is not permitted, or when running in environments like Azure App Service web apps where direct TCP connections might be limited. While simpler to configure, it often has slightly higher latency and lower throughput compared to direct mode. Preferred regions. In a globally distributed Cosmos DB account, you can specify an ordered list of preferred Azure regions. The SDK will automatically attempt to connect to the nearest specified region first. If that region is unavailable or experiences issues, it will gracefully fail over to the next preferred region. This intelligent routing ensures low-latency access for users worldwide. Custom retry options. As mentioned, you can fine-tune the default retry behavior, such as setting a different maximum number of retries or adjusting the backoff strategy. Request timeout. You can set a global timeout for all operations, ensuring that requests don't hang indefinitely. Properly configuring these options based on your application's deployment environment, network constraints, and performance requirements is crucial for building a highly optimized and resilient solution. 4.8 Practical example. Setting up a basic application to connect and verify connectivity. Let's consider a conceptual example of a simple application that connects to Cosmos DB and verifies its connectivity. While we won't show direct code blocks, the steps and concepts apply across most SDKs. Imagine you're building a basic user management service. Application configuration. Store your Cosmos DB endpoint URL and primary key, or connection string in your application's configuration file or environment variables. For local development, this might point to your Cosmos DB emulator. Initialize the client. At the very start of your application, e.g., upon application bootup in a web application, or in the main function of a console app, create a single instance of the Cosmos client. Use the configuration values loaded in Step 1. Get database and container references. Use the Cosmos client to obtain references to your database and a specific container, for example, your user's container. These references can also be created once and then reused throughout your application. Perform a simple operation, verification. To verify connectivity, you might perform a very basic, inexpensive operation. For instance, attempt to read an item that you know exists or doesn't exist and check for a 404 not found response, or simply read the properties of your container. Handle success and failure. If the operation succeeds, it confirms your application can communicate with Cosmos DB. If it fails, catch the exception or error. Check the HTTP status code. A 401 unauthorized might indicate incorrect keys, while network-related errors would suggest connectivity issues. Cleanup for console apps. In a short-lived application like a console script, remember to dispose or close the Cosmos client instance when your application shuts down to release resources properly. For long-running server applications, this is typically handled by the application framework. This basic setup serves as the foundational layer upon which all your subsequent data operations will be built. You now have the programmatic tools to fully interact with your Cosmos DB resources, paving the way for performing actual CRUD operations, which is the subject of our next chapter. Chapter 5, Performing CRUD Operations. Interacting with your data. 5.1, The Fundamentals of Data Interaction. Why CRUD operations are core. At the heart of any database interaction are the fundamental operations that allow applications to manage data. These operations are collectively known by the acronym CRUD: create, adding new data to the database; read, retrieving existing data from the database; update, modifying existing data; delete, removing data from the database. These 4 operations form the bedrock of almost every application, providing the means for users to input information, view it, change it, and remove it. In Azure Cosmos DB, performing these CRUD operations efficiently and effectively is paramount to building performant and cost-effective applications. While the concepts of CRUD are universal across databases, Cosmos DB offers specific ways to perform them that leverage its distributed nature and JSON document model. Understanding these specifics, and especially the nuances of their request unit, RU, consumption, is key to optimizing your application. We will explore how your application, using the SDKs discussed in the previous chapter, will interact with your Cosmos DB documents. 5.2, Creating new items. Inserting documents into your data store. Creating a new item, document. In Azure Cosmos, DB involves sending a JSON document to a specified container. Each item must have a unique id property within its logical partition, and it must also specify the value for its partition key. When you create an item, you are essentially providing the full JSON payload that you wish to store. The SDK takes this JSON object, serializes it, and sends it to the Cosmos DB service. The RU cost for creating an item is generally proportional to the size of the document, in kilobytes, and the complexity of its properties, as Cosmos DB automatically indexes all properties by default, unless configured otherwise, which we'll discuss in Chapter 9. Larger documents and those with more complex, deeply nested structures will consume more RUs for creation. For example, if you are adding a new user to your user's container, your application would construct a JSON object representing the user's profile, and then use the SDK's createItemAsync, or equivalent method, passing the item and the partition key value. Key considerations for item creation. Uniqueness of id and partition key. Cosmos DB enforces that the combination of id and partition key value must be unique within a container. Attempting to create an item with an id that already exists within the same logical partition will result in a conflict, HTTP 409 error. Id property. While Cosmos DB can generate an id if you don't provide one, it's generally best practice to provide a meaningful id for your documents. This id is crucial for point reads and for easily identifying specific documents. 5.3 Reading items. The power and efficiency of point reads. Retrieving data from Cosmos DB can be done in two primary ways: performing queries, which we will cover in Chapter 6, or performing point reads. For single item retrieval, point reads are by far the most efficient and cost-effective method. A point read is an operation where you retrieve a single item by providing its unique id and its partition key value. Since Cosmos DB knows exactly where that specific item is stored, the physical partition, it can fetch it directly without scanning an index or traversing data. Lowest RU cost. Point reads are the cheapest operations in Cosmos DB. They often consume as little as 1 RU, making them ideal for high-volume, single-item lookups, e.g., fetching a user profile by userid or a product by productid. The exact RU cost depends on the size of the document, but it's always significantly lower than a query for the same item. Lowest latency. Because no complex logic or index lookups are involved, point reads offer the lowest possible latency. Practical tip. Whenever your application needs to retrieve a specific single document and you know its id and partition key, which should be the case if you designed your data model correctly, always opt for a point read. Avoid using a select from C where CID equals sumid query if you can perform a point read. The query will be more expensive and slower, even if only one item is returned, because it involves the query engine and index lookup. Example: fetching a user profile document using its userid, assuming user id is the partition key, and its id your application would call read item async or equivalent, passing in the id and partition key value. 5.4 Updating documents. Full replacement versus targeted patch operations. Cosmos DB offers two primary ways to update existing documents. Full document replacement. This is the most straightforward method. You retrieve the existing document, make your changes to the JSON object in your application code, and then send the entire modified document back to Cosmos DB using a replace item async or equivalent method. Simplicity, easy to implement. High RU cost. The RU cost is similar to creating a new document, as the entire document is rewritten. This can be inefficient if you're only changing a small field in a large document. Optimistic concurrency. This method often works hand in hand with e-tags to prevent lost updates, as discussed in the next section. Targeted patch operations, partial updates. For scenarios where you only need to modify specific properties or elements within a document, Cosmos DB supports patch operations. This allows you to apply changes to only the relevant parts of a document without sending the entire document payload. Efficiency significantly reduces RU consumption and network payload, especially for large documents where only a few fields are changing. Atomic operations. Patch operations are atomic, meaning multiple changes within a single patch only succeed entirely or fail entirely. Supported operations. Patch operations typically support adding new fields, modifying existing fields, removing fields, incrementing numeric values, and removing elements from arrays. When to use patch operations: incrementing a counter, e.g., view count on an article. Updating a specific address field within a nested address object. Adding an item to an array, e.g., a new tag to a product's tags array. Practical example: updating a user profile. Imagine a user document. If a user changes their email address, using a patch operation to update only the email field is much more efficient than replacing the entire user document, especially if the user document also contains large objects like deeply nested preferences or activity logs. Deciding between full replacement and patch operations depends on the nature of your update. If you're fundamentally altering the structure or most of the content of a document, full replacement is fine. If you're making small, targeted adjustments, patch operations are the more performant and cost-efficient choice. 5.5 Deleting items. Removing data safely and efficiently. Deleting an item in Azure Cosmos DB is a straightforward operation. You typically provide the item's id and its partition key value to the SDKs delete item async or equivalent method. Similar to point reads, Deleting an item by its id and partition key is a highly efficient operation with a low RU cost. Considerations for deletion. Permanent removal. Deleting an item permanently removes it from the container. There's no recycle bin for deleted Cosmos DB items, so exercise caution. Logical deletion. For some applications, particularly those requiring auditing or soft deletes, you might implement a logical delete instead of a physical one. This involves adding a flag to the document, e.g., is deleted. True rather than removing it. Your application logic would then filter out logically deleted items. While this increases storage, it preserves history. Time to live, TTL. As an alternative to programmatic deletion, Cosmos DB offers an automatic expiration feature called Time to Live, TTL. You can set a default TTL value at the container level and/or specify a TTL for individual items. Once the TTL expires, Cosmos DB automatically deletes the item, freeing up storage and RUs. This is incredibly useful for transient data like sessions, event logs, or temporary caches. 5.6 Understanding optimistic concurrency control with e-tags. Ensuring data integrity. In a distributed, multi-user environment, ensuring data integrity can be challenging. Imagine two users simultaneously trying to update the same document. Without a mechanism to prevent this, one user's changes might accidentally overwrite another's, leading to a lost update. Azure Cosmos DB uses optimistic concurrency control, OCC, implemented through e-tags, entity tags, to prevent such issues. Here's how it works. E-tag on every document. Every document in Cosmos DB has an ETAG property. This e-tag value is a unique identifier that changes every time the document is modified. Read and store e-tag. When your application reads a document, it also receives its current e-tag value. Provide e-tag on update delete. When your application attempts to update or delete that same document, it provides the e-tag value it read earlier. Service checks e-tag. Cosmos DB compares the e-tag provided by your application with the current e-tag of the document in the database. Match. If the e-tags match, it means the document has not been changed by anyone else since your application read it. The update-delete operation proceeds successfully, and a new asterisk e-tag is generated for the modified document. No match. If the e-tags do not match, it means another client has modified the document in the interim. Cosmos DB rejects your operation with a precondition failed HTTP 412 error. What to do on e-tag mismatch, 412 error. When you receive a 412 error, your application knows that its attempt to modify the document was based on an outdated version. The standard approach is to reread the latest document. Fetch the most recent version of the document from Cosmos DB. Reapply changes. Reapply your intended modifications to this fresh version of the document. Retry operation. Attempt the update-delete operation again with the new e-tag. This retry logic can sometimes be encapsulated within your application's data access layer. OCC with e-tags is a powerful yet simple mechanism that provides strong data integrity guarantees without resorting to costly locking mechanisms typical of pessimistic concurrency. It assumes that conflicts are rare, hence optimistic, and only handles them when they occur. 5.7 Transactional batch operations. Atomic multi-item updates within a partition. While individual item operations, create, read, replace, delete, are atomic, what if you need to perform multiple operations that must succeed or fail together, like a single transaction? Cosmos DB offers transactional batch operations that allow you to group multiple point operations, create, upsert, read, replace, delete, patch into a single atomic transaction. Key characteristics and limitations. Atomic, all operations in the batch succeed or fail as a single unit. If any operation in the batch fails, the entire batch is rolled back. Single logical partition. Crucially, all operations within a transactional batch must target items that belong to the same logical partition. You cannot create a batch that spans multiple logical partitions. This is a fundamental design principle of Cosmos DB, as cross-partition transactions are significantly more complex and resource-intensive in a globally distributed system. Cost-effective. While individual operations might still incur RUs, the batch operation itself is often more efficient than making multiple separate calls, and it provides atomicity guarantees. Use cases. Transferring funds between two bank accounts within the same partition, e.g., using a counted as partition key for both. Updating a user's profile and simultaneously adding an entry to their activity log, where both items belong to the same user's logical partition. Adding multiple items to a shopping cart that is modeled as a single logical partition, e.g., carted as the partition key for all line items. Transactional batch operations provide a powerful tool for ensuring data consistency for related items that reside within the same logical partition, mimicking the transactional capabilities users expect from a reliable database. 5.8 Efficient data loading, the bulk support feature for high throughput. For scenarios involving high-volume data ingestion or migration, performing individual CRUD operations one by one can be slow and inefficient, leading to high latency and potentially underutilizing your provisioned throughput. To address this, the Azure Cosmos DB SDKs offer bulk support or bulk executor library. This feature is designed to maximize the throughput of your operations by allowing you to send many operations, creates, updates, deletes, to Cosmos DB in a single batch, intelligently distributing them across partitions and leveraging parallel processing. Parallelism. The bulk feature uses internal parallelism to send operations concurrently to different physical partitions within your Cosmos DB account. Throttling handling. It intelligently handles throttling, 429 errors, internally by retrying operations with appropriate backoff, greatly simplifying the code you need to write for high-volume ingest. Reduced latency. By batching and paralleling requests, you can achieve significantly higher throughput and lower overall latency for large-scale data operations compared to sequential individual operations. Use cases. Initial data migration into Cosmos DB. Batch importing product catalogs or user lists. Periodic data synchronization from another system. Archiving or deleting large sets of old data. While not suitable for real-time, low-latency, single-item transactions, the bulk feature is indispensable for scenarios that require processing large volumes of data efficiently and quickly. 5.9 Real-world application. Managing user profiles, a CRUD example walkthrough. Let's tie these concepts together with a practical, albeit conceptual, example of managing user profiles in a hypothetical web application. Assume our user's container has user id as its partition key, and each user document has a unique id, which might also be the user id. Scenario 1. New user registration, create. When a new user signs up, the application collects their details, name, email, password hash, etc. It constructs a JSON document for the new user, ensuring id is unique and user id is set for the partition key. The SDKs create item async, user document, new user id method is called. If id already exists within that partition, a 409 conflict error is returned, indicating a duplicate user, e.g., duplicate email tied to a user id. Scenario 2, displaying user profile point read. When a logged-in user visits their profile page, the application needs to quickly retrieve their data. It uses the logged-in user's user id as both the id and the partition key for the read item async, user id method. This is a highly efficient point read, consuming minimal RUs and returning the user's full profile almost instantly. The ETAG of the document is noted for future updates. Scenario 3. Updating user email address, patch operation with OCC. A user wants to change their email address. The application reads the user's latest profile, Scenario 2, obtaining the current ETAG. It prepares a patch operation to replace only the email field. The SDKs patch item async, user id, patch operations, request options with ETAG method is called. If another process had updated the user's profile between the read and the patch operation, e.g., admin changed their name, the ETAG comparison would fail, and a 412 precondition failed error would be returned. The application would then reread, reapply the change, and retry. Scenario 4. Deactivating user account, partial update logical delete. Instead of fully deleting, the application deactivates accounts for auditing. The application reads the user's profile and obtains the current EDAG. It prepares a patch operation to set isActive to false and deactivation date to the current time. The SDKs patch item async, userid, patch operations, request options with EDAG method is called. Alternatively, if accounts auto-expire, the application could set a TTL property on the document, and Cosmos DB would eventually remove it. Scenario 5. Admin bulk user import bulk operation. An administrator needs to import 10,000 new user profiles from an external system. The application collects all 10,000 user JSON documents. It uses the SDKs bulk support feature, adding create item operations for all 10,000 documents to a bulk operation batch. The bulk operation is executed, and the SDK efficiently streams the requests in parallel to Cosmos DB, handling any throttling internally. This ensures the import completes much faster and more reliably than 10,000 separate create item async calls. By understanding and correctly applying these CRUD operations, along with features like point reads, patch, optimistic concurrency, and bulk support, you can build highly efficient, performant, and reliable applications on Azure Cosmos DB. In the next chapter, we'll delve deeper into how to retrieve data using Cosmos DB's powerful SQL-like query language. Chapter 6. Querying data with the SQL API. Beyond simple reads. 6.1. The Cosmos DB SQL API. Your gateway to complex data retrieval. While point reads, retrieving an item by its id and partition key, are the most efficient way to access a single item, most complex applications require retrieving sets of items based on various criteria. This is where the Azure Cosmos DB SQL API comes into play. Despite being a NoSQL database, Cosmos DB offers a powerful and flexible SQL-like query language that allows you to perform rich, declarative queries over your JSON documents. This SQL dialect is specifically designed for JSON documents, supporting nested properties, arrays, and subqueries. It's not identical to ANSI SQL used in relational databases, but it's very familiar, making it easy for SQL-savvy developers to pick up quickly. The SQL API allows you to filter documents based on property values, project-specific fields to optimize payload size, order results, aggregate data e.g. count, sum, average, work with arrays and nested objects. Crucially, every query you execute consumes request units, RUs. The complexity of your query, the amount of data scanned, and the efficiency of your indexing strategy, which we will cover in Chapter 9, directly impact the RU cost. The goal is always to write queries that are both expressive and cost-effective. 6.2 Basic Queries. Select, from, where clauses for fundamental data selection. The foundation of the Cosmos DB SQL API queries remains familiar to anyone with SQL experience. Select clause specifies which fields or expressions the query should return. Select C, id, c.name from C, returns only the id and name properties of each document. Select from C returns the entire JSON document, means all properties. Select value c.name from C returns only the value of the name property, not as a JSON object, but the raw value. This is useful for simple lists. From clause denotes the collection container from which to retrieve data. The C, or any alias you choose, represents the current document being processed. From C, all documents in the current container. Where clause filters the documents based on specified conditions. Where C status equals active, only documents where the status property is active. Where C age 18, documents where the age property is greater than 18. Example: retrieving active users. Select C, id, C first name, C, last name, C email. From C, where C status equals active, this query would efficiently return a list of active users, projecting only their id, first name, last name, and email address, reducing the data payload. 6.3 Filtering data effectively. Operators and powerful built-in functions. The where clause supports a rich set of operators and built-in functions to enable precise filtering of your JSON documents. Comparison operators: equals, 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 less or equal, standard equality and comparison. In checks if a value is present in a list of values, where C. Category in electronics, home goods. Between checks if a value falls within a range, where C. price between 100 and 500. Logical operators, and or not, combine or negate conditional expressions, where C. status equals active, and C. last login 2023 to 1 to 0, 1 T000Z. String functions. Cosmos DB provides many useful string functions for filtering and projecting. Contains source substring, checks if a string source contains a substring. Where contains C. description, waterproof. SDRESWITH, source prefix, checks if a string source starts with a prefix. Where starts with C. name Azure. Ends with source suffix, checks if a string source ends with a suffix. Lower stringexpr, upper stringexpr, convert case, useful for case-insensitive comparisons. Where lower C. product name equals smartphone. Numeric functions: floor, ceiling, round, ABS, SQRT, standard mathematical functions. Array functions. Crucially, Cosmos DB SQL API is powerful for querying array data within your JSON documents. ARRAYSUNTIONS, array, value, checks if an array contains a specific value. Where array contains C. tags, gaming. Returns documents where the tags array contains gaming. ARRAYLENGTH array returns the number of elements in an array, where array length C. comments 0. Example: products in multiple categories with certain tags. Select C. id C. name C. price. From C. Where C. category in electronics, gadgets, and array contains C. features Bluetooth. 6.4 Working with arrays in queries. Extracting and filtering nested data. JSON documents often contain nested objects and arrays, which the Cosmos DB SQL API handles seamlessly. You can directly access properties of nested objects using dot notation, e.g., C address city. Querying arrays, as briefly seen with ARRAYSUNTIONS, is a common requirement. Beyond simply checking if an array contains a value, you can often flatten or iterate over arrays using a special kind of join operation. This join is not a traditional relational join. Instead, it creates a Cartesian product of each document with each element of the specified array. This can be very powerful for querying data within arrays, but it can be expensive in terms of RUs if not used carefully, especially on very large arrays. Example: finding users who have purchased a specific product in their orders array. Assume a user document like id user123, name Alice, orders orderid, O1 producted, P101 quantity 1, orderid O2 producted, P202 quantity 2. To find users who bought P101, select C, id C. name O orderid. From C, join O and C orders. Where O. producted, P101. Here, join O and C orders iterates through each order object, O, within the C orders array for every document. This effectively allows you to filter and project based on properties within array elements. 6.5 Aggregation functions. Summarizing and analyzing your data. Cosmos DB SQL API supports common aggregation functions, allowing you to perform analytical queries to summarize data within a container. Count returns the number of items or non-null values. Select Count CID from C where C status equals active, count active users. Select Count 1 from C, count all documents in a container. Sum calculates the sum of a numeric property. Select Sum C total orders from C where C region equals USA. AVG calculates the average of a numeric property. Select AVG C rating from C. Min returns the minimum value of a numeric property. Select Min C price from C where C category equals books. Max returns the maximum value of a numeric property. Select Max C stock from C. Important note on aggregations and partitioning. Aggregations typically involve scanning all documents that match the where clause. If your query spans multiple logical partitions, e.g., it does not include your partition key in the where clause, The aggregation will be performed across all partitions, which can be computationally expensive and incur high RU costs. For large datasets and frequent analytical aggregations, consider offloading such queries to analytical stores or using a dedicated analytical solution like Azure Synapse Link, discussed in Chapter 11, rather than directly running them within your transactional Cosmos DB container. 6.6. Efficient pagination with offset limit and continuation tokens. For web or mobile applications, displaying a large set of query results at once is often impractical. Instead, you'll paginate the results, showing only a subset, a page, at a time. Cosmos DB offers two primary ways to paginate: offset and limit, or top. This is similar to traditional SQL pagination. Offset skips a specified number of items, and limit, or top, returns the next specified number of items. Select from C order by C timestamp offset 10 limit 5, skip first 10, return next 5. Caveats with offset limit. Expensive for deep paging. While easy to use, offset limit is generally not recommended for deep paging, retrieving pages far into the results set on large datasets. This is because the database still has to process and then discard all the items before the offset point. The RU cost increases linearly with the offset. Less performant, the performance degrades as the offset increases. Use offset limit for simple paging with small page sizes and when the total number of items is relatively small, or for next previous type buttons rather than direct page number selection. Continuation tokens, recommended for production paging. This is the most efficient and recommended way to paginate in Cosmos DB. When you execute a query, the SDKs response includes a continuation token if there are more results. To get the next page of results, you simply pass this token back with your next query request. How it works. The continuation token is an opaque string that Cosmos DB uses to bookmark the exact point in the results set where the previous query left off. This means the service doesn't have to rescan from the beginning. Highly performant, provides fast and efficient paging regardless of how deep you are in the result set. Low RU cost. Each page fetch is essentially a new query that starts from the specific bookmark, making it very efficient in terms of RU consumption. Ideal for load more scenarios. Perfect for user interfaces that support load more buttons or infinite scrolling. Practical application. When implementing paging for user-facing applications with potentially large result sets, always prioritize using continuation tokens for efficiency and low RU cost. 6.7. Understanding cross-partition queries and strategies to minimize their impact. As discussed in Chapter 8, your data in Cosmos DB is distributed across logical and physical partitions based on your chosen partition key. Targeted queries, single partition. The most efficient queries are those that include the partition key in their where clause, e.g., select from C where C.userid equals user 123. Cosmos DB knows exactly which logical partition to target, reducing the scan scope and RU cost significantly. Cross-partition queries. Queries that do not include a partition key in their where clause, or use operators that inherently require scanning all partitions, like without SDARTSWITH on the beginning of a string, or aggregations without filtering on partition key, must be broadcast to all physical partitions. Each partition executes the query, and the results are then aggregated and returned to the client. Impact of cross-partition queries. Higher RU cost. They consume substantially more RUs because every partition must be scanned. The RU cost grows proportionally with the number of physical partitions. Higher latency. Aggregating results from multiple partitions introduces additional latency. Can lead to throttling. If you have many physical partitions and run frequent cross-partition queries, you can quickly exhaust your provisioned throughput. Strategies to minimize cross-partition query impact. Prioritize partition key in queries. Design your data model and access patterns so that your most frequent queries involve a known partition key. This means most of your queries should be targeted at a single logical partition. Batch processing for analytical loads. For analytical queries that inherently require scanning a large portion of your data, e.g., how many active users are there in total? Consider running them as infrequent batch jobs during off-peak hours or using Azure Synapse Link, Chapter 11, for true analytical workloads. Consider denormalization. Sometimes, denormalizing data to make it accessible within a single partition can avoid a cross-partition query. For example, if you frequently need to retrieve comments for a post, you might embed some post metadata in the comment document, allowing you to query comments by posted, assuming comment document is partitioned by posted. Limit results. Use top or limit with an order by clause to reduce the amount of data returned, even from cross-partition queries, though this doesn't reduce the scan costs. Enable cross-partition query. You must explicitly set this option in the SDK. Enable cross-partition query equals true, or use the Azure Portal's Data Explorer to run cross-partition queries. This acts as a safeguard, forcing you to acknowledge the potential cost implications. 6.8 Server-side logic, stored procedures, triggers, and user-defined functions, UDFs, for transactional code. For situations requiring more complex transactional logic or data transformations directly within the database, Cosmos DB provides support for server-side programmability using JavaScript. These features allow you to execute code directly on the database engine. Stored procedures, atomic transactions. All operations within a single stored procedure execute as a single, ACID-compliant transaction. If any operation fails, the entire transaction is rolled back. Batch operations can perform multiple operations, CRUD, within a single request, but they are limited to a single logical partition context. Use cases. Complex business logic, atomic multi-document updates on the same partition, enforcing data integrity constraints. Example: atomically enrolling a student in a course, which might involve updating the student document and creating a new enrollment document, assuming both are in the same partition. Pre-triggers, execute before an item operation, create, update, delete. Use cases: input validation, data manipulation, e.g., setting a created@at timestamp, generating a unique ID if not provided, enforcing business rules before data is saved. Example: a pre-trigger ensuring that a user's email address is correctly formatted and unique before a new user document is created. Post-triggers, execute after an item operation. Use cases: auditing, generating derived data, sending notifications, integrating with external systems, though often the change feed is a better choice for external integration. Example: a post-trigger that logs every document modification to an audit trail container. User-defined functions, UDFs, custom functions designed for use within a SQL query. Use cases: complex calculations, custom string manipulations, data transformations that cannot be achieved with standard SQL functions. Example: a UDF that calculates a discounted price based on complex logic not easily expressed in pure SQL, which can then be used in a select or where clause. Important considerations for server-side logic. JavaScript execution. All server-side logic is written in JavaScript. Single partitions scope, generally. Stored procedures and triggers operate within the context of a single logical partition. While UDFs can be used in cross-partition queries, the functions themselves operate on data within the single document they are evaluating. Resource consumption. Server-side scripts consume RUs, and long-running or complex scripts can time out 5 seconds default. Keep them lean and focused. Debugging. Debugging server-side JavaScript can be challenging. Extensive logging and careful testing are crucial. Change feed alternative. For initiating external processes or maintaining materialized views, the change feed, Chapter 10, is often a more scalable and reliable solution than post-triggers. 6.9 Querying best practices for developers. Optimizing performance and cost. To get the most out of Cosmos DB SQL API, follow these best practices. Always filter by partition key when possible. The single most impactful optimization. Queries that target a single logical partition are the most efficient. Project only necessary fields, select CID, see .name versus select. Reduce network payload and deserialization overhead by returning only the data your application needs. Understand RU costs. Regularly check the RU charge for your queries, especially new ones. Optimize expensive queries. Efficient indexing, Chapter 9. Ensure appropriate indexes are in place to support your query patterns. A query might have a low RU cost but take a long time if it's not supported by an index. Conversely, a query might be fast but very expensive if it requires a full scan. Limit offset limit for deep paging. Use continuation tokens for robust pagination. Limit cross-partition queries. Minimize their use, especially on large, busy collections. If unavoidable, monitor their RU consumption closely. Prefer point reads. For single item retrieval, read item async is always superior to a select query. Test with representative data. Test your queries against data sets that accurately reflect your production data volume and distribution. Understand consistency models. Asterisk the chosen consistency model can impact query performance and RU costs. We will delve into this in the next chapter. By internalizing these querying principles, you'll be well equipped to design and implement applications that retrieve data from Azure Cosmos DB efficiently, cost-effectively, and with optimal performance. Chapter 7, Consistency Models Demystified, Choosing the Right Balance. 7.1, Distributed Systems, and the ever-present challenge of consistency. In the world of single-server applications, maintaining data consistency is relatively straightforward. All reads and writes go to the same location, making it easy to ensure that everyone sees the same, most up-to-date version of the data at all times. However, distribute that data across multiple servers, data centers, or even continents, as Azure Cosmos DB does, and the challenge of consistency becomes significantly more complex. In a globally distributed system, data is replicated across many nodes and regions to ensure high availability and low latency. The moment you have multiple copies of data, you face a fundamental question. When a piece of data is updated in one location, how quickly and reliably do those changes propagate to all other copies? And what guarantees can you make about the data that different users might read from different locations? This is the heart of consistency in distributed databases. Striking the right balance between how consistent your data needs to be versus how available and performant your system can be is a critical design decision for any application leveraging distributed databases. 7.2, the CAP theorem, a foundational principle for understanding distributed databases. Before diving into Cosmos DB's specific consistency models, it's helpful to understand a foundational concept in distributed systems, the CAP theorem. Often attributed to computer scientist Eric Brewer, CAP states that a distributed data store can only ever deliver 2 out of 3 desirable properties. Consistency. Every read receives the most recent write or an error. All nodes see the same data at the same time. Availability. Every request receives a non-error response without guarantee that it contains the most recent write. The system is always up and responsive. Partition tolerance. The system continues to operate despite arbitrary numbers of messages being dropped or delayed by the network between nodes. In a distributed system, network partitions are an unavoidable reality. The CAP theorem suggests that you must sacrifice one of these properties for the other two. Since network partitions are inevitable in large-scale distributed systems, P is a given. The real-world trade-off is often between consistency and availability. Databases built for high availability and global scale often prioritize availability and partition tolerance over strict consistency, allowing for what's known as eventual consistency. Others prioritize strong consistency, potentially at the expense of availability or latency during network disruptions. Azure Cosmos DB is unique because it pushes the boundaries of the CAP theorem by offering 5 well-defined consistency models, allowing developers to choose the specific trade-off that best suits their application's needs. This granular control is a powerful feature that distinguishes Cosmos DB from many other distributed databases. 7.3, Cosmos DB's 5 consistency models. An overview of your choices. Azure Cosmos DB provides a spectrum of 5 consistency models, ranging from the strongest, strong, to the weakest, eventual. Each offers different guarantees regarding how data changes are propagated and seen by your application, directly impacting latency, throughput, and availability. Let's explore each one, starting from the strongest. 7.4 Strong consistency, when absolute order and immediate readability are paramount. Strong consistency provides the highest level of data consistency you can achieve. With strong consistency, ACID guarantees. All reads are guaranteed to return the very latest committed version of the data, regardless of the region from which the read is performed. This is equivalent to ACID, atomicity, consistency, isolation, durability, properties found in traditional relational databases. Global synchronization. Every write operation must be replicated and committed across all configured regions before it's considered complete. This ensures that any subsequent read from any replica will see that latest write. Global order. Strong consistency guarantees that clients read data in the order it was written in a globally consistent manner. Trade-offs. Highest latency. Because every write must wait for all replicas to acknowledge the commit, latency is highest. For multi-region accounts, the write latency is dictated by the round-trip time to the furthest region. Lower throughput. The coordination required across all replicas can reduce the maximum write throughput. Reduced availability, potentially. If one of the configured regions for global replication becomes unavailable, write operations may halt until that region recovers or is removed from the replication set. When to use strong consistency. Use strong consistency for scenarios where data integrity and seeing the absolute latest version of data are non-negotiable, even at the cost of higher latency or reduced throughput. Case study. Financial transaction systems. Imagine a global financial application managing bank accounts. If a user transfers funds from account A to account B and immediately checks the balance of account A from a different region, they must see the updated lower balance. There can be no ambiguity or delay. A financial transaction system, where even a slight inconsistency could lead to significant financial discrepancies, demands strong consistency. For instance, if you're updating a stock portfolio or processing payment transactions across multiple regions, you need absolute guarantees that all reads reflect the latest write, ensuring no race conditions or lost updates. The higher latency is an acceptable trade-off for data integrity. Anecdote: critical gaming leaderboard. Consider a highly competitive, global online game. If a player achieves a new high score, that score must immediately and unequivocally be reflected as the highest score on the leaderboard for all players, regardless of their geographical location. Any delay or inconsistency could undermine the fairness and competitive integrity of the game. Strong consistency would be chosen to ensure absolute global ordering of scores for displaying the definitive global leaderboard. 7.5 Bounded staleness. A practical balance of consistency and performance. Bounded staleness offers a balance between strong and weaker consistency models. It guarantees that reads are not too stale by defining acceptable bounds for how out-of-date read data can be. You can configure bounded staleness using two parameters. Number of versions, K. Reads are guaranteed to reflect a version that is at most K versions behind the latest. Time interval T. Reads are guaranteed to reflect a version that is at most T seconds behind the latest. Whichever of these two thresholds is met first, the replica will serve the read. If the bound is exceeded, the client waits for the replica to catch up with the primary write region. Trade-offs: lower latency than strong. Writes don't need to wait for all regions to commit, only until they are within the defined bounds. Higher throughput than strong, reduced coordination overhead. Guaranteed consistency within bounds. Your application can define its acceptable level of staleness. When to use bounded staleness. Ideal for applications that require ordered reads and writes, but can tolerate a small degree of data staleness for better performance. It provides high availability with a known upper bound on inconsistency. Example: a personalized news feed where articles must appear in chronological order and the feed needs to be relatively up-to-date. A few seconds or a few versions of delay are acceptable for better responsiveness. 7.6 Session consistency. The developer's default friend for user experience. Session consistency is the most commonly used consistency model and often the default for single-region Cosmos DB accounts. It provides guarantees that are intuitively comforting for a single user session. Within a single client session, session consistency guarantees: read your writes. If you write data, any subsequent read requests within the same session will immediately see that write. Monotonic reads. After reading data, version A, you'll never read an older version, version B, where B is older than A's. Monotonic writes. All write requests from the same session are guaranteed to be written in the order they were issued. Write follows reads. If you read version A of an item, then write to it, your write is guaranteed to be applied to a version that is at least A or newer. Crucially, these guarantees apply only within a single client session. If two different users or two different sessions interact with the same data, they might observe eventual consistency between them. Trade-offs. Excellent balance. Offers a great balance of consistency, low latency, and high throughput for most common application patterns. Comfort for users. Ensures a consistent experience for individual users interacting with their own data. When to use session consistency. This is the preferred consistency level for most applications that involve user interactions, such as shopping carts, typical web applications, and mobile apps. It gives the user a strong sense of consistency for their own actions. Case study, blog comments or social media feeds. For the blog post example from Chapter 2, if a user posts a comment, they expect to see their comment immediately appear on the post page. This is guaranteed by session consistency. Another user viewing the same post from a different session might see that comment a fraction of a second later, eventual consistency between sessions. But the user who wrote the comment will always see their own write reflected instantly. This creates a predictable and reliable user experience without the overhead of strong consistency. 7.7 Consistent prefix. Guaranteed ordering without imposing strict latency. Consistent prefix is a subtle but important consistency model. It guarantees that reads will never see out-of-order writes. If a sequence of operations is A, B, C, you are guaranteed to read A, B, or A, B, C. You will never read A, C, missing B, or C, B, A out of order. No rollbacks. You will never see a value roll back to an earlier state. Data only moves forward in time. Potential staleness. While order is guaranteed, there's no bound on how much behind the latest write a read might be, unlike bounded staleness. Trade-offs. Higher availability and throughput than session strong. No cross-region coordination or session state tracking required between different sessions. Lower latency than session strong. Reads can be served from the nearest replica without waiting for full replication. When to use consistent prefix. This model is useful for scenarios where you need to ensure the ordering of events but can tolerate some degree of staleness, and where the performance or availability constraints are tighter than what session consistency can offer. Examples include log analysis, streaming data processing where the order of events is critical, but extreme recency isn't. An application might care that events are processed in order, but doesn't need to wait for every single event to be propagated to all readers before continuing. 7.8 Eventual consistency. Maximizing throughput and minimizing latency for high-volume workloads. Eventual consistency is the weakest consistency model, but also the most performant and available. No order guarantees. Reads might reflect a very stale version of the data. Future reads will eventually catch up, but there are no guarantees about the order of updates. You might read different versions of the same item from different replicas or even out-of-order writes. Highest throughput. Because writes do not need to wait for replication, they are instantly acknowledged, maximizing write throughput. Lowest latency. Reads are served from the nearest replica instantly, regardless of its synchronization state. Highest availability. The system remains available for both reads and writes even during network partitions or replica failures. Trade-offs. Potential for high staleness. This is the primary trade-off. Reads might return data that is significantly out of date. When to use eventual consistency. Choose eventual consistency for scenarios where the system can easily tolerate stale data and raw performance, high availability, and maximum throughput are top priorities. Example, IoT telemetry ingestion. Consider an IoT solution collecting millions of sensor readings per second. Each reading is a time-stamped event. The system needs to ingest this data as quickly as possible without any bottlenecks. While the analytic dashboards will eventually be updated, seeing a sensor reading from a few seconds ago is perfectly acceptable. The sheer volume and need for high throughput make eventual consistency the ideal choice for data ingestion. Anecdote: social media like counts. On a social media platform, when a user likes a post, that action needs to be registered quickly. The total like count may not need to be precisely accurate across all users at every single millisecond. A slight delay in the global like count refreshing is acceptable. The platform prioritizes ingesting millions of likes per second and showing some count to the user, knowing that all replicas will eventually converge to the correct total. 7.9. Choosing the right consistency level for your application. A decision framework. Selecting the appropriate consistency model is a crucial architectural decision. It's rarely a one-size-fits-all answer for an entire application. Different parts of your application, or even different operations on the same data, might require different consistency levels. Here's a decision framework. Understand your data's requirements. Is it mission-critical, financial, or legally binding? E.g., bank transactions, inventory counts lean towards strong. Can you tolerate some bounded staleness for better performance? E.g., personalized news feeds, relatively up-to-date analytics. Consider bounded staleness. Is the data specific to a user session where they expect to see their own rights immediately? E.g., user profiles, shopping carts, typical UI interactions. This is the sweet spot for session consistency. Does the order of events matter but not extreme recency? E.g., log streams, activity feeds where sequence is key, consistent prefix. Do you prioritize maximum ingest rate and lowest latency, even if reads are eventually consistent? E.g., IoT data, user activity logging, high-volume real-time feeds where minor delays are fine, eventual consistency. Evaluate performance implications. Latency. Strongest equals highest, eventual equals lowest. Throughput. Strongest equals lowest, eventual equals highest. RU cost. Generally, weaker consistency models can offer slightly lower RU costs for read operations. Consider availability needs. Strong consistency can reduce write availability in multi-region setups if a key region goes down. Weaker consistencies offer higher write and read availability. Start with session consistency, often a good default. For most new applications, session consistency provides an excellent balance of guarantees and performance for a pleasant user experience. If you hit performance bottlenecks or have stricter requirements for specific data, then evaluate moving to stronger or weaker consistency models for those particular operations. By carefully evaluating these trade-offs, you can pick the consistency model that aligns perfectly with your specific use case, optimizing your application for performance, cost, and user experience. 7.10. Overriding consistency. Granular control for specific operations and edge cases. A powerful feature of Azure Cosmos DB SDKs is the ability to override the default consistency level at the request level. This means that even if your container is configured for session consistency, the default, a particular read operation could temporarily request strong consistency, or a write operation might specify eventual consistency if the application logic demands it. How it works conceptually. When you perform an operation, e.g., read item async, query definition create iterator, the SDK methods often accept an optional request options object. Within this object, you can set the consistency level property for that specific request. Example use case. Imagine an inventory management system using session consistency as its default. When a user confirms adding an item to their cart, session consistency is fine. However, a separate, critical process that performs an end-of-day reconciliation of global inventory might temporarily request strong consistency for its reads to ensure it gets the absolute latest, globally synchronized count before reporting. This mechanism allows for fine-grained control, optimizing performance where it's needed while ensuring strict accuracy for critical operations. While this capability provides immense flexibility, use it judiciously. Overriding consistency too frequently or without clear justification can complicate development, testing, and debugging. Nevertheless, it's a valuable tool in your Cosmos DB development toolkit for handling edge cases and optimizing specific, critical workflows within your application. Understanding and effectively applying Cosmos DB's consistency models is critical for building robust, high-performance, and globally scaled applications. Our next chapter will delve into another crucial aspect of scalability: partitioning. Chapter 8, Partitioning for Performance and Scale, the Key to Success. 8.1, The Need for Horizontal Scaling and Distributed Data in Modern Applications. In the early days of computing, scaling a database typically meant vertical scaling, upgrading to a more powerful server with more CPUs, RAM, and faster storage. While effective to a point, this approach eventually hits physical and economic limits. There's only so much power you can pack into a single machine. Modern applications, especially those supporting millions of users globally or ingesting vast amounts of data, like IoT telemetry, demand a different approach: horizontal scaling. This involves distributing data and workload across many smaller commodity servers, allowing the system to grow almost infinitely by simply adding more machines. Azure Cosmos DB is fundamentally built on this principle of horizontal scaling. It automatically distributes your data and throughput across a collection of servers called physical partitions. To do this efficiently, it needs a way to intelligently decide where each piece of data should live. This mechanism is called partitioning. Understanding partitioning is not just an optimization. It's arguably the most critical design decision you'll make when building a Cosmos DB solution. A well-chosen partition key is the foundation for achieving the low latency, high throughput, and elastic scalability that Cosmos DB promises. A poorly chosen one can lead to bottlenecks, higher costs, and performance issues that are difficult to remedy later. 8.2, Understanding Logical and Physical Partitions in Cosmos DB. Before diving into the partition key, let's clarify the distinction between logical and physical partitions, as Cosmos DB manages both. Logical partition. A logical partition is a conceptual division of your data in a Cosmos DB container, uniquely identified by the value of your chosen partition key. All items, documents, that have the same value for the partition key belong to the same logical partition. For example, if you choose userid as your partition key, then all documents for userid equals Alice reside in one logical partition, all documents for userid Bob reside in another, and so on. Cosmos DB ensures that all items within a single logical partition are stored together on the same physical partition, or replica set of physical partitions. This guarantees ACID transactions for items within the same logical partition. A single logical partition has a storage limit, currently 20 GB. Physical partition. A physical partition represents the actual underlying storage and compute resources, SSD-backed storage, CPU, memory, that host one or more logical partitions. Cosmos DB automatically manages physical partitions. When you provision throughput for your container, Cosmos DB provisions the necessary physical partitions to handle that throughput. As your data grows or your throughput requirements increase, Cosmos DB transparently adds more physical partitions. Each physical partition has its own limits on throughput, e.g., typically max 10,000 RUS and 50 GB storage. Cosmos DB hashes the partition key value to determine which physical partition a logical partition should reside on. Essentially, your logical partitions are how you choose to group your data, and physical partitions are where Cosmos DB actually stores and serves that data. Cosmos DB intelligently maps logical partitions to physical partitions. 8.3, The all-important partition key, your data's address in a distributed world. The partition key is a property that exists in every document within your Cosmos DB container. Its value determines the logical partition an item belongs to. When you create a new container, you define the partition key path, e.g., user id, product id. Choosing the right partition key is paramount because it dictates how your data is distributed and how operations are routed. Consider a user profile container. If you select UserID as the partition key, all user-related documents for a specific user, e.g., user Alice, will reside in the same logical partition. When your application needs data about Alice, it provides UserID equals Alice in the request. Cosmos DB can then directly route the request to the physical partition containing Alice's data, leading to a fast and efficient single partition operation, point read or query. If your application frequently performs queries that filter on the partition key value, e.g., get all orders for a specific customer, these queries are highly efficient because they hit only one logical and physical partition. Queries that do not specify a partition key or those that span multiple partition key values become cross-partition queries, which are significantly less efficient and more costly, as they fan out to query all physical partitions. 8.4 Characteristics of an effective partition key: high cardinality and even distribution. A good partition key has two primary characteristics: high cardinality. The partition key should have a large number of unique values. For example, UserID in a system with millions of users has high cardinality. Gender, on the other hand, would have low cardinality, male, female, other, and would be a very poor partition key as it would group too much data into too few logical partitions. High cardinality ensures that there are many potential logical partitions to distribute data across. Even distribution of RUs and data, this is the more crucial aspect. An effective partition key should distribute both the storage and, more importantly, the request volume, RUs, as evenly as possible across all logical partitions during peak times. Data distribution. A key that evenly distributes data prevents any single logical partition from exceeding its 20 GB storage limit, or causing the underlying physical partition to become overloaded purely by data volume. Throughput distribution. This is even more important. An ideal partition key prevents hot partitions, logical partitions that receive a disproportionately high amount of requests, reads, or writes compared to others. If one physical partition is handling significantly more RUs than others, it can become a bottleneck, leading to throttling for queries that target that partition, even if your overall provisioned RUs for the entire container is sufficient. 8.5 Avoiding hot partitions and understanding the logical partition size limit. Hot partitions. A hot partition occurs when a single logical partition, or the underlying physical partition hosting it, receives a significantly higher volume of requests, RUs, than other partitions. This can happen if low cardinality key. Choosing something like city as a partition key means all users from a large city, e.g., New York, will be in one logical partition. If traffic to users in New York spikes, that partition can become hot. Sequential key. Using a monotonically increasing key like timestamp or orderid, if it's truly sequential, can funnel all new writes to a single logical partition for a period, making it hot. Tenant-specific overload. In a multi-tenant application, if one tenant, whose tenanted is the partition key, experiences a massive surge in usage while others are relatively quiet, that tenant's partition can become hot. When a physical partition hosting a hot logical partition hits its throughput limit, e.g., 10,000 RUs, all requests directed to that logical partition will be throttled, HTTP 429 errors, leading to application performance degradation. Cosmos DB cannot automatically rebalance requests within a single logical partition to another physical partition. Logical partition size limit, 20 GB. Each logical partition also has a maximum storage size of 20 GB. While less common to hit than RU limitations, if a single logical partition, e.g., all data for a single user, if your partition key is UserID, grows beyond 20 GB, you'll encounter storage errors. This enforces the need for high cardinality to ensure data is spread out. 8.6 Strategies for choosing the right partition key for your application. Choosing the optimal partition key is an iterative process. Here are common strategies and considerations. Prioritize your most frequent query pattern, read-heavy systems. If your application frequently queries by a specific property, that property is often an excellent candidate for a partition key. Example, For a user profile system where most lookups are by userid, then userid makes perfect sense. All of a user's data can reside together, enabling efficient single-partition reads. Ensure even distribution of request volume, write-heavy systems. For applications with high write throughput, the key must distribute writes evenly. Good. Sessionid for analytics data, deviceid for IoT telemetry, orderid for e-commerce orders, if orderid varies sufficiently. Bad. Date all writes on a given day go to one partition. Status, only a few values. Composite partition keys. If a single property doesn't provide enough cardinality or even distribution, you can create a composite partition key by combining multiple properties. This forms a synthetic partition key. Example: in a multi-tenant application where users belong to a tenant, tenanted is a good first step. But if one tenant might grow immense, you could combine tenanted with userid to form the partition key. Tenant id user id. Note: the partition key in Cosmos DB is a single string value, so you combine them in your application to form a single string, like tenant a user 123. This ensures individual users within a tenant are also well distributed. Use synthetic partition keys when natural keys are insufficient. Sometimes, the natural properties of your data don't lend themselves to a good partition key. In such cases, you might create a synthetic key. Example: if you have millions of small documents that are very rarely queried individually, but often processed in batches, and no natural key works, you might use a random number or hash as part of the partition key, e.g., hashifid %100. This ensures even distribution, but means most queries become cross-partition. This is a trade-off for high ingest rate when query patterns are very flexible. Consider write patterns for time series data. For time series data, e.g., sensor readings, a common pattern is to use a composite key involving the device ID and a timestamp bucket, e.g., device IDEMMDD. This distributes writes across different days' devices while enabling efficient retrieval of all data for a specific device on a specific day. 8.7 Synthetic partition keys. When a single property isn't enough for optimal distribution, a synthetic partition key is created by concatenating multiple properties of your document to form a single string value. This is useful when a single property doesn't provide enough cardinality or distribution for the workload. Your most common query pattern involves filtering on a combination of properties, and placing them together in the partition key allows for efficient single partition queries. Example: multi-tenant application with tenant-specific user IDs. Consider an application where users belong to specific tenants. User IDs might be unique within a tenant, but not globally. If you query users primarily by userid and tenanted, a synthetic partition key like tenant iuser ID would be effective. Partition key: tenant a user 123. This ensures all data for user 123 belonging to tenant A goes to the same logical partition. When you query for user 123 within tenant A, you provide the full tenant iuser ID as the partition key, resulting in a highly efficient single partition query. If you only used userid as the partition key, and different tenants could have the same userid, e.g., tenant A has user 123, tenant B has user 123. Then querying for user 123 without specifying the tenant would become a cross-partition query. 8.8 Practical partitioning examples. Designing for users, products, and IoT telemetry. Let's illustrate with concrete examples. User profiles / user-specific data. Scenario: application displays user profiles, user settings, user activities. Most queries are by a single user. Partition key: userid. Reasoning: high cardinality, millions of users. All data for a single user goes to one logical partition, enabling efficient point reads and single partition queries. Rarely would you need to query all users across the system for a simple profile lookup. Product catalog. Scenario: e-commerce site with products categorized. Products are looked up by producted, but also frequently by category. Option 1, simple, producted. Pros: good for direct product lookups. Cons: queries like all products in electronics category would be cross-partition queries, potentially expensive. Option 2, optimized for category queries. Category name. Pros, efficient for all products in category, queries. Cons, if a single category, e.g., accessories, has millions of products or receives disproportionately high traffic, it could become a hot partition, both data size and RUs. Queries by product did need to include category in their where clause or become cross-partition. Hybrid/synthetic. If products and categories are both critical access paths, denormalization might be used. You might combine category name and product id into a synthetic key, or accept some cross-partition queries, or use two containers with different partitioning strategies linked by application logic. This illustrates that sometimes there's no single perfect key, and you choose based on the most common critical access pattern. IoT telemetry data. Scenario: devices sending sensor readings every minute. Need to ingest millions of readings per second and retrieve readings for a specific device over a time range. Good partition key. Device-id or a synthetic key like device idate bucket, e.g., device 123 to 2023 to 10 to 26. Reasoning: ingesting by device-id spreads writes across all active devices. Retrieving data for a specific device is a single partition query. Adding a date bucket component ensures that if a single device generates a massive amount of data, its data for a specific day doesn't exceed the 20 GB logical partition limit. Queries for a specific device for a specific day are still single partition. Bad partition key. Sensor type or timestamp, monotonically increasing, and low cardinality sensor type. These would concentrate writes to a few partitions, making them hot. 8.9 The consequences of a poor partition key choice and how to approach remediation. A poorly chosen partition key can manifest as excessive throttling, HTTP 429 errors. Specific operations or applications start failing because a hot partition cannot handle the load, even if the overall RUs provisioned are adequate. High RU consumption for simple queries. Queries that you expect to be cheap become very expensive because they frequently perform cross-partition scans. Slow query performance, due to throttling or the overhead of cross-partition operations. Logical partition size limits hit. You're unable to write more data for a specific logical partition because it has reached 20 GB. Remediation for a poor partition key. This is the challenging part. The partition key cannot be changed for an existing container. To correct a poor partition key choice, you typically need to create a new container with the corrected, optimal partition key definition. Migrate existing data. Write a data migration script. This script will read data from the old container and insert it into the new container using the new partition key. This can be a time-consuming and resource-intensive process, especially for large datasets. Leverage the change feed, Chapter 10, on the old container to capture ongoing changes and apply them to the new container during the migration, minimizing downtime for writes. Use bulk support, Chapter 5, when writing to the new container to maximize throughput during migration. Update application code. Modify your application to use the new container and its new partition key strategy for all operations. Cut over traffic. Once data is synced and tested, redirect your application traffic to the new container. Deprecate old container. Once confident, delete the old container. This process can be complex and involve downtime, highlighting why careful consideration of the partition key before extensive data population is paramount. In conclusion, the partition key is your most powerful tool for ensuring that your Azure Cosmos DB solution scales effectively and cost-efficiently. Invest the time upfront to understand your data access patterns, identify potential hotspots, and choose a partition key that evenly distributes both your data and your anticipated request unit volume. This foundational decision will have a profound impact on the success of your Cosmos DB-powered application. Chapter 9, Indexing and Cost Optimization, Making Your Database Efficient. 9.1, The Crucial Role of Indexing in Performance and Cost Efficiency. In any database, indexing is fundamental to efficient data retrieval. Without indexes, a database would have to scan every single record to find the data requested by a query, a full scan, or table scan. This is incredibly slow and resource-intensive for large datasets. Indexes are special lookup tables that allow the database to quickly locate data without scanning the entire collection. Much like an index in a book, helps you find information without reading every page. In Azure Cosmos DB, indexing plays a particularly crucial role for two main reasons. Query performance. Proper indexing ensures that your queries run quickly and return results with low latency. Cost efficiency, RU consumption. Queries that can efficiently use an index consume significantly fewer request units, RUs, than those that require a full scan. As RUs are your billing currency, efficient indexing directly translates to lower operational costs. Cosmos DB takes a unique approach to indexing, balancing developer convenience with powerful customizability. 9.2 Automatic Indexing. Cosmos DB's Smart Default and its capabilities. One of Azure Cosmos DB's most notable features is its automatic indexing capability. By default, when you create a new container, Cosmos DB automatically indexes every property of every document. This includes nested properties within JSON objects and elements within arrays. This index everything default is incredibly convenient, as it means you can start querying your data immediately after inserting it without needing to define indexes upfront. Convenience. Developers can iterate rapidly without worrying about index maintenance. Flexibility. You can evolve your data model and add new properties to documents without needing to update indexing policies. New properties are automatically indexed. Performance. For many workloads, especially those with diverse query patterns or where the cost of write operations is less critical, automatic indexing provides good query performance out of the box. However, this convenience comes with trade-offs. Higher write costs. Indexing every property consumes more RUs during write operations, creates, updates. Cosmos DB has to update the indexes for every change. More storage. The index itself consumes storage space. For very large documents or extremely high-volume write workloads, this can become a consideration. For development, testing, and many applications with moderate write volumes, the default automatic indexing works well. But for high-performance, cost-optimized production scenarios, fine-tuning your indexing policy is essential. 9.3 Custom Indexing Policies. Tailoring indexes for your unique query patterns. While automatic indexing is a great starting point, you can define custom indexing policies to optimize for specific performance or cost requirements. A custom indexing policy allows you to explicitly include or exclude certain properties or paths within your JSON documents from the index. The goal of custom indexing is to reduce write RUs. By not indexing properties that are never queried, you save RUs on every write operation. Reduce index storage. Less data in the index means less storage consumed. Improve query performance for specific queries. While automatic indexing handles most lookups, certain complex query patterns, like order by on multiple properties or geospatial queries, require explicitly defined specific index types. You define indexing policies as part of your container settings. The policy is a JSON document that specifies included paths, excluded paths, and index types. Important note: the partition key path, my partition key and see my partition key, is always indexed by default and cannot be removed from the index. It's fundamental to data routing, not just querying. 9.4 Types of indexes. Range, spatial, and composite for diverse data access needs. Cosmos DB supports different types of indexes, optimized for various data types and query patterns. Range index, default. Applicability: numeric, string, Boolean, and null values. Usage: supports equality queries, equals, range queries, equals, less or equal, and order by clauses. It's the most common index type and is used by default for all indexed paths. Example, where cprice100 order by c.name. Spatial index. Applicability: geospatial data points, polygons, multipolygons, represented in GeoJSON format. Usage: enables efficient spatial queries like SDDISDNCE, SDWITHIN, SDINTRSCTS. Example, where est within, clocation, polygon, where location is a GeoJSON point. Composite index. Applicability, multiple properties. Usage, crucial for queries that involve a where clause with multiple equality filters and an order by clause or a range filter with an order by clause. It combines the order of multiple properties into a single index. Example, select from C where C.category equals electronics order by cprice desk. For this query to be performant, a composite index on category price desk would be highly beneficial. Without it, the where clause might use an index, but the order by would likely require sorting in memory, consuming more RUs. Creating a composite index. You define a composite index as an ordered list of paths with an ascending, or descending order. The order of the paths in the composite index definition matters. Indexing mode, consistent. Included paths, path / excluded paths, path, some big text property, exclude large text fields not queried. Composite indexes. A first composite index, path category order, ascending, path price order, descending. A second composite index, path first name order, ascending. A paths, last name order, ascending. 9.5, including and excluding paths. Fine-tuning your index for optimal storage and performance. Custom indexing policies give you granular control over what gets indexed. Included paths, by default, included paths is set to path / meaning everything is indexed. You can remove this default and explicitly list only the paths you want to index. When to include paths. Any property you routinely use in where clauses for filtering. Any property you use in order by clauses. Properties used in aggregation functions. Properties used in join clauses for subqueries. Excluded paths. These are properties or paths that you explicitly tell Cosmos DB not to index. This is extremely valuable for large text fields. If you have large text blobs, e.g., product descriptions, log messages, that you primarily store and retrieve but rarely query, e.g., no full-text search, excluding them from the index can significantly reduce write RUs and index storage. Properties never queried. Any property that is only used for display purposes or retrieved via point reads, where index is not needed. High cardinality unique identifiers that aren't the id, e.g., a session token that is always retrieved by id and partition key. Example exclude path. Indexing mode, consistent. Included paths, path / index everything by default. Excluded paths, path, some large description field. Don't index this large text field. Path, internal use only. Don't index this property. When you define excluded paths, always remember to also include a broad included path like, unless you explicitly want to define every single path to be indexed. Otherwise, nothing would be indexed by default. Changing indexing policies in a live container will trigger an index transformation, which runs in the background and consumes some RUs but does not impact availability. 9.6, analyzing query execution and request units. Understanding your query's footprint. To effectively optimize your queries and indexing, you need to be able to analyze their performance. Cosmos DB provides the request unit, RU, charge as a primary metric, but there's more to it than just the number. Request units, RUs, every query or operation returns the RU charge. This tells you the cost. Too high RU. If a query consumes many RUs, it signals inefficiency. Inconsistent RUs. If the same query against similar data has wildly different RU charges, it might indicate throttling or an issue with how the query is distributed. Query metrics / query plan, the SDKs, and the Data Explorer in the Azure portal can often provide more detailed query metrics beyond just the RU cost, often in the form of a query plan or diagnostics. This plan explains: index utilization. Did the query use an index? Which one? Scan versus seek. Did it perform a full scan or an efficient index seek? Document count. How many documents were scanned versus how many were returned? Cross-partition activity. Was it a single partition or cross-partition query? Logical versus physical reads indicates how much data was processed. Using the Data Explorer. In the Azure portal's Data Explorer, when you run a query, you'll see a Query Stats tab next to the Results tab. This provides the RU cost execution time, and details on index utilization. Leverage this heavily during development and testing. Using the SDKs. The SDKs provide methods to retrieve query metrics within the response object or through diagnostic flags. It's good practice to log these metrics for critical queries, especially in production, to monitor performance trends. Example: if a query returns a high RU cost and the query plan shows a full scan of the container rather than an index seek, it's a clear indication that either a required index is missing or the query needs to be rewritten to utilize an existing index. 9.7 Throughput Management. Manual versus auto-scale, provisioning for cost-effective scaling. Beyond indexing, managing your container's throughput, RUS, is another critical aspect of cost optimization. This was briefly introduced in Chapter 3, but let's dive deeper into how to choose and manage it effectively. Manual throughput. Concept: you explicitly set a fixed RUS value for your container or database, e.g., 400 RUS, 10,000 RUS. Pros: highly predictable cost. You pay for what you provision, regardless of usage. Cons: can lead to throttling if workload exceeds provisioned RUS, or wasted cost if provisioned RUs are consistently underutilized. Best for workloads with extremely stable and predictable patterns, or when you have a strict, unchanging budget. Autoscale throughput. Concept: you define a maximum RUS, e.g., 4,000 RUS. Cosmos DB automatically scales your throughput between 10% of this maximum and the maximum based on your usage. Pros: prevents throttling during traffic spikes by automatically scaling up and saves cost during quiet periods by scaling down. You only pay for the highest RUS used within that hour, up to your defined maximum. Cons: cost is less predictable than manual, can fluctuate hour by hour. Minimum cost is 10% of maximum. Best for workloads with variable, unpredictable, or bursty traffic patterns. This is often the recommended choice for most applications to balance cost and performance. Tips for throughput management. Start with autoscale. For new projects, autoscale is often the safest starting point to avoid throttling while staying cost-efficient. Monitor usage. Use Azure Monitor Graph Explorer to track your actual RU consumption against your provisioned throughput. This data is invaluable for fine-tuning. Adjust seasonally. If your application has predictable traffic seasonality, e.g., higher during business hours, lower at night, you can programmatically adjust your autoscale max RUS using the Azure SDKs or Azure CLI PowerShell, saving costs. Database-level vs. container-level throughput. Container-level throughput gives each container its own dedicated RU budget and guarantees. Best for mission-critical containers or if you have specific high-traffic containers. Database-level throughput. All containers in the database share a common RU budget. More cost-effective if you have many containers whose aggregate workload is predictable, but individual container usage fluctuates. A busy container can consume RUs, potentially leaving other containers short. Use carefully. 9.8 Optimizing RU costs. Strategies for a leaner Azure Cosmos DB bill. Beyond indexing and throughput management, here are other strategies to reduce your RU consumption and overall Cosmos DB bill. Prefer point reads. As discussed in Chapter 5, retrieving a single item by its ID and partition key is the cheapest operation, often 1 RU. Avoid cross-partition queries. Queries that span multiple logical partitions are significantly more expensive. Design your data model partition key to minimize them. Project only necessary fields in queries. Select C, ID, C.name from C costs less than select from C because the payload is smaller. Choose the right consistency model. Weaker consistency models generally provide lower RU costs for read operations. Eventual consistency offers the lowest latency and highest throughput with the lowest RU cost at scale, while strong consistency provides the highest consistency at the highest RU cost. Use time to live, TTL. Automatically expire transient data, e.g., session state, old logs. This not only frees up storage, but also saves RUs by offloading the deletion process to Cosmos DB's background tasks. Leverage bulk execution. For high-volume writes or data migrations, the bulk executor library is much more efficient per RU than individual operations. Server-side logic, stored procedures, triggers. For atomic, multi-item operations within a single partition, using a stored procedure might be more RU efficient than multiple round trips from the client to the database. Compress data, application side. If you store large documents, close to the 2 MB limit, and their content is compressible, e.g., large JSON objects with repetitive keys or text data, consider compressing the data before storing it in Cosmos DB and decompressing it on retrieval. This can reduce RU consumption, as RUs are generally based on item size and storage. However, this adds CPU overhead to your application. Monitor and write size. Continuously monitor your actual RU consumption using Azure Monitor. Adjust your provisioned throughput up or down to align with your needs. Don't over-provision, but also don't under-provision to the point of constant throttling. 9.9 Resource Governance. Capping your query costs to prevent spikes. For critical queries, especially those that might be user-defined or have unpredictable parameters, you can implement resource governance to set a maximum request unit, RU, charge for a single query. This is a client-side setting within the SDK that protects your application from unusually high RU consumption from a single query. If a query exceeds the specified maximum RU, the SDK will cancel the query and return an error, though it might still consume RUs up to the cap. Why use it? Cost control. Prevents runaway queries from consuming an exorbitant amount of RUs and unexpectedly spiking your bill. Performance protection. Helps prevent single, inefficient queries from degrading overall database performance or leading to throttling for other, more critical operations. User experience. For reporting tools or ad hoc queries, it gives a clear indication when a user's query is too broad or inefficient, prompting them to refine it. You would typically set this using query options within the SDK when executing a query iterator. 9.10 Advanced Indexing Scenarios. Geospatial and graph indexing considerations. While the focus has been on document data with the core SQL API, Cosmos DB's multi-model nature extends to its indexing capabilities. Geospatial indexing. If your application stores location data, e.g., users' current position, property listings, and needs to perform queries like find all users within a 10 km radius, or check if a point is within a polygon, you would configure a spatial index. This index is optimized for efficient two-dimensional data queries using standard GeoJSON types. Graph indexing with Gremlin API. When using the Gremlin API for graph data, Cosmos DB automatically indexes all properties of vertices and edges. The Gremlin API queries are then processed efficiently against this graph index. These advanced indexing capabilities highlight Cosmos DB's flexibility in handling diverse data types and query patterns within a single, highly performant service. By diligently managing your indexing policies, understanding your throughput needs, and consistently monitoring RU consumption, you can ensure your Azure Cosmos DB solution remains performant, scalable, and cost-effective throughout its lifecycle. The next chapter will explore the change feed, a powerful feature for building event-driven solutions. Chapter 10, The Change Feed, Building Event-Driven Solutions. 10.1, Event-Driven Architectures and the Rise of Reactive Systems. Modern applications often demand real-time responsiveness, seamless integration, and the ability to react instantly to data changes. This has led to the increasing popularity of event-driven architectures, EDAs. In an EDA, components communicate by emitting and reacting to events, notifications that something significant has occurred. Instead of one system constantly polling another for updates, the system generating the data change simply broadcasts an event, and interested parties subscribe to these events and react accordingly. This architectural style offers numerous benefits. Decoupling. Components are loosely coupled, meaning they can evolve independently without tightly affecting others. Scalability. Event producers and consumers can scale independently. Real-time processing enables immediate reactions to changes, powering real-time dashboards, notifications, and analytics. Resilience. Systems can be more fault-tolerant. If a consumer fails, the event often remains available for later processing. Azure Cosmos DB is uniquely positioned within this architectural paradigm through its powerful feature known as the change feed. 10.2. Introducing the Azure Cosmos DB change feed, your real-time data stream. The Azure Cosmos DB change feed is a persistent, ordered, append-only log of all changes that happen within a Cosmos DB container. Anytime an item is created, updated, or deleted, a record of that change is added to the change feed. Think of it as a continuous, unbounded stream of events representing every modification to your data. Key characteristics of the change feed. Persistent. Changes are retained indefinitely by default, so consumers can process them at their own pace or replay them from a specific point in time. Ordered. Changes are guaranteed to be in the order in which they occurred for a given logical partition. Cross-partition order is not guaranteed, but sequential reads within a logical partition are always maintained. Append-only. The change feed is a log. You can only read from it, not modify it. Real-time. Events are available with near-zero latency, allowing applications to react almost instantly. Per partition. Each logical partition in your container has its own independent stream of changes. The change feed provides a highly reliable and scalable mechanism to track and act upon changes in your Cosmos DB data without impacting your operational database's performance. 10.3 Why and when to use the change feed. Practical scenarios for your applications. The Azure Cosmos DB change feed opens up a vast array of possibilities for building reactive and integrated solutions. Here are some common and powerful scenarios where the change feed proves invaluable. Real-time analytics and dashboards. Scenario: you need a dashboard that displays near real-time metrics about your application's data, e.g., live order counts, user activity. How change feed helps. As new orders or user actions are updated in Cosmos DB, the change feed captures these events. A consumer, e.g., an Azure function, Stream Analytics, can process these events, update aggregated metrics, and push them to a real-time dashboard or another analytical store. Materialized views. Scenario: your primary data model is optimized for transactional writes, but you need a highly optimized view for specific, complex read patterns that might be expensive with direct queries. How change feed helps. The change feed can be used to denormalize your data into a separate container, or another database system like Azure Cache for RDS, Azure SQL Database, or Azure Data Explorer that is specifically optimized for a particular read pattern. For example, if your user data is partitioned by userid, but you frequently need to query all users who signed up in the last hour, the change feed could update a user sign-up hourly summary container or a specialized search index. Data synchronization to other systems. Scenario: you need to keep another system, e.g., a search engine, a data warehouse, a legacy database, an external API, continuously updated with changes from your Cosmos DB data. How change feed helps. The change feed acts as an ETL, extract, transform, load pipeline. When data changes in Cosmos DB, a consumer picks up the change, transforms it into the format required by the external system, and loads it. Practical case study from planning. Building a real-time search index. Imagine an e-commerce platform where product details are stored in Cosmos DB. Users search for products using Azure Cognitive Search. The change feed can automatically update the Cognitive Search Index. When a product's price, description, or availability changes in Cosmos DB, the change feed triggers an Azure function. This function then takes the updated product document, formats it for cognitive search, and pushes the changes, ensuring the search results are always fresh and accurate the moment data changes in Cosmos DB. Auditing and logging. Scenario: you need to maintain an immutable log of all data changes for compliance, debugging, or historical analysis. How change feed helps. Every change event from the change feed can be written to an audit log container, an Azure storage account, or an Azure data lake. This provides a complete, ordered history of changes. Sending notifications and alerts. Scenario: triggering notifications, email, SMS, push notifications, or alerts based on specific data conditions, e.g., order status changes, inventory levels dropping. How change feed helps. A consumer can listen for specific events, e.g., order status equals shipped, and then use a notification service, e.g., Azure Communication Services, send CRUD to alert users. 10.4 The Change Feed Processor Library, your scalable consumption engine. While you can technically read from the change feed manually, the recommended and most robust way to consume changes in a scalable and fault-tolerant manner is by using the change feed processor library. This library is available for various SDKs, Net, Java, Node.js, Python, and significantly simplifies the consumption process. The change feed processor library handles load balancing and parallel processing. It automatically distributes the processing of logical partitions across multiple consumer instances, allowing you to scale out your processing power. Checkpointing. It keeps track of the last processed point in the change feed, ensuring that even if a consumer instance fails, it can resume processing from where it left off without missing any changes or reprocessing too much data. Error handling and retries. It manages transient errors and retries for you. Lease management. It uses a lease container to coordinate processing across multiple consumer instances. 10.5 Understanding the lease container. Managing change feed state and progress. The lease container is a special container, just a regular Cosmos DB container, often within the same database as your source container, that the change feed processor library uses to manage its state. Its primary functions are distributed coordination. When you have multiple instances of your change feed processor, e.g., multiple Azure Function App instances, the lease container helps them coordinate which logical partitions each instance is responsible for. Each logical partition in the source container gets a corresponding lease document in the lease container. Checkpointing progress. As a change feed processor instance processes events for a logical partition, it periodically updates the lease document for that partition to record the continuation token, or a timestamp, of the last successfully processed change. This is its checkpoint. Fault tolerance. If a change feed processor instance crashes or loses connectivity, another instance, or the same instance when it restarts, can pick up the lease for the logical partitions it was processing. It then reads the last checkpoint from the lease document and resumes processing from that point, ensuring no data is lost and no unnecessary reprocessing occurs. Scalability. When you scale out your change feed processor instances, e.g., increasing the number of Azure Function instances, the leases are automatically rebalanced across the available instances, effectively distributing the workload. You provide the change feed processor library with references to both your source container, the one generating changes, and your lease container. The lease container needs to exist before your processor starts. 10.6 Processing changes. Implementing your developer's callback function. At the heart of the change feed processor is a delegate or callback function that you implement. This function is invoked by the library whenever a new batch of changes from the change feed becomes available for processing. Your callback function receives a list of documents or items that have changed, contextual information like the lease token for the partition. Within this function, you write the business logic that defines how your application reacts to the data changes. This could involve writing to another database, updating a materialized view, writing to an audit log, calling an external API, triggering a notification or updating an external system, pushing to a message queue event bus, sending an event to Azure Event Hubs or Service Bus for further processing by other microservices, performing aggregations, updating counts or sums for real-time dashboards. The change feed processor library ensures that your callback function is invoked reliably and efficiently as changes occur. 10.7 Fault tolerance and scalability of the change feed processor. Ensuring reliability. The change feed processor library is designed to be highly fault-tolerant and scalable. Resilience to failures. If an instance of your change feed processor crashes, the leases it held will expire. Other active instances will detect this and automatically claim those expired leases, resuming processing from the last checkpoint. This ensures continuous processing without manual intervention. Automatic load balancing. As you add or remove instances of your change feed processor, the library automatically rebalances the processing workload leases across the available instances. This allows you to dynamically scale your processing power up or down based on the volume of changes in your Cosmos DB container. Handling throttling. The library internally handles any throttling 429 errors received from Cosmos DB during change feed reads, applying backoff logic and retrying, so your application code doesn't need to implement these complexities. Ordered processing per logical partition. While the change feed doesn't guarantee global order, it always guarantees order within a logical partition. The change feed processor always processes changes for a single logical partition sequentially, preventing any out-of-order processing issues for a given entity. Restart from any point. You can configure the change feed processor to start reading from the beginning of the feed, from beginning, from the current moment, from now, or from a specific continuation token. This is useful for replaying events for debugging, disaster recovery, or building new materialized views. 10.8. Building a real-time analytics dashboard with change feed as its backbone. Let's expand on a practical scenario. Building a real-time analytics dashboard for an e-commerce application. Goal: display the number of new orders placed in the last hour, live updates to total sales, and the most popular products in near real time. Architecture. Cosmos DB source container. The orders container stores all customer orders as documents, partitioned by orderid or customerid. Change feed processor, Azure function. An Azure function with a Cosmos DB trigger listens to the change feed of the orders container. Its binding uses the change feed processor library. Processing logic inside Azure function. When the function receives a batch of changed order documents, it iterates through them. For new orders, is new order flag or check if it's a create operation. It increments a counter for orders in last hour. It updates running totals for total sales by summing order total amount. For each product in an order, it increments a counter for product sales count. Reporting store, e.g., Azure Cache for Redis, blob storage, or another Cosmos DB container. The Azure function writes these aggregated metrics to a suitable storage. For a real-time dashboard, Azure Cache for Redis might be used for fast read access to simple counters. For more complex aggregations history, a separate Cosmos DB container, e.g., metrics, might store hourly summaries. Dashboard application. A web application or mobile app periodically queries the reporting store to refresh its dashboard display. Flow. Customer places an order new document inserted into orders container in Cosmos DB change feed picks up the new order. Azure function is triggered function extracts relevant data, order total, product IDs. Function updates counters in Azure Cache for Redis dashboard refreshes and displays updated real-time metrics. This illustrates how the change feed forms the backbone of a responsive, event-driven system, allowing you to react to transactional data changes and populate analytical views without impacting the performance of your core operational database. 10.9. Common pitfalls and best practices for change feed development. While powerful, watch out for these common pitfalls. Ignoring logical partition ordering. Remember, order is guaranteed per logical partition. It's not a global order. If your processing logic depends on global order, you'll need additional mechanisms, e.g., external queues with timestamps, to reorder events, which adds complexity. Too much logic in the processor. The change feed processor is a consumer. Keep its logic lean. If processing is complex, push events to a message queue, event hubs, service bus for asynchronous processing by other microservices. Lease container throughput. Ensure your lease container has enough provisioned throughput to handle the checkpoints and coordination of your processor instances. If it's too low, it can become a bottleneck. Misunderstanding TTL versus delete. The change feed shows deleted items, but not items expired via TTL. If you need to react to TTL expired items, you'll need to query for them separately or design your application differently. Idempotency. Your processing logic should ideally be idempotent, meaning that processing the same event multiple times produces the same result as processing it once. While the change feed processor handles checkpoints, scenarios like network issues or restarts might result in processing a small number of duplicate events. Your logic should be able to handle this gracefully, e.g., check if a record already exists before inserting. Monitoring. Monitor your change feed processor instances for errors and latency. Azure Monitor provides metrics for change feed consumption. The Azure Cosmos DB change feed is a transformative feature for building modern, reactive applications. By understanding its capabilities and leveraging the change feed processor library, you can unlock powerful event-driven patterns that enhance your application's responsiveness, scalability, and integration capabilities without sacrificing the performance of your core database. Chapter 11. Integrating Cosmos DB with other Azure services. 11.1. The Azure Ecosystem. Cosmos DB as a central hub for your data. Azure Cosmos DB is not an island. While it's a powerful database service on its own, its true potential is unlocked when seamlessly integrated with the broader Azure ecosystem. Microsoft Azure provides a comprehensive suite of cloud services, each designed for a specific purpose, ranging from compute and networking to analytics, AI, and developer tools. When you integrate Cosmos DB with other Azure services, you can build complete end-to-end solutions. Leverage specialized services optimized for different parts of your application's architecture, e.g., serverless compute, real-time analytics, AI. Offload non-database tasks. Delegate tasks like data processing, messaging, or security to services explicitly built for them, allowing Cosmos DB to focus on what it does best. Fast, globally distributed data storage. Enhance capabilities. Add features like full-text search, stream processing, or advanced analytics that are not core database functionalities but are crucial for a fully featured application. Simplify development and operations. Use Azure's managed services to reduce the operational burden, focusing more on your application's unique value proposition. This chapter will highlight key Azure services that frequently integrate with Azure Cosmos DB, showcasing how they complement each other to build powerful and scalable cloud-native applications. 11.2. Real-time processing with Azure Functions and the change feed trigger. Azure Functions is Azure's serverless compute service, allowing you to run small, event-driven pieces of code, functions, without explicitly provisioning or managing servers. Its native integration with Azure Cosmos DB is incredibly powerful, especially when combined with the change feed. How they integrate. Cosmos DB trigger. Azure Functions provides a native Cosmos DB trigger. This trigger automatically invokes your Azure function whenever new changes appear in your Cosmos DB container's change feed. The function simply receives a batch of changed documents as input. Input and output bindings. Azure Functions also offer input and output bindings for Cosmos DB. This means your function can easily read documents from or write documents to Cosmos DB containers with minimal code. You define the binding in the function's configuration, e.g., function JSON file or attributes decorators in code. And the Azure Functions runtime handles the boilerplate code for connecting to Cosmos DB. Common scenarios. Real-time synchronization. As seen in Chapter 10, an Azure function triggered by the change feed can synchronize data to other systems, e.g., Azure Cognitive Search, Redis, blob storage, or to different data models within Cosmos DB itself. Data processing transformation. Process incoming data or transform it before storing it in another system. For example, validating, enriching, or aggregating data before it's persisted in a secondary data store. Notifications and alerts. Trigger functions to send emails via SendGrid, SMS messages, via Twilio, or push notifications to mobile apps when specific data changes occur, e.g., order status updates, new user registrations. Event-driven workflows. Chain multiple functions together or send events to other messaging services, event hubs, service bus, to kick off more complex business processes. Azure Functions provide a highly scalable, consumption-based way to build reactive consumers for Cosmos DB's change feed, making it effortless to implement real-time processing without managing servers. 11.3. automating workflows with Azure Logic Apps and Power Automate. For developers and business users who prefer a low-code or no-code approach to workflow automation, Azure Logic Apps and Power Automate, part of Microsoft Power Platform, offer intuitive visual designers for orchestrating workflows. How they integrate: connectors. Both Logic Apps and Power Automate have a rich set of connectors for various services, including Azure Cosmos DB. These connectors expose actions, e.g., get an item, create an item, query documents, and triggers, e.g., when a document is created or modified via the change feed. Visual Workflow Designer. You can design complex workflows by dragging and dropping actions, setting conditions, loops, and parallel branches without writing traditional code. Common scenarios: business process automation. Automatically update a CRM record when a user profile changes in Cosmos DB, or initiate an approval workflow when a new order is placed. Data governance. Trigger an alert when a document type is created that violates a compliance rule. Scheduled tasks. Run daily reports from Cosmos DB data and email them to stakeholders. Simple data integration. Move data between Cosmos DB and other SaaS applications as part of a business flow. While less code-centric than Azure Functions, Logic Apps and Power Automate are excellent for rapidly prototyping integrations and automating business processes where a visual workflow is preferred. 11.4 Analytics at Scale with Azure Synapse Analytics Link. Bridging operational and analytical worlds. Traditionally, performing deep analytics on operational databases like Cosmos DB required extracting ETL data into a separate data warehouse or data lake. This process could be time-consuming, expensive, and lead to data staleness. Azure Synapse Analytics Link for Cosmos DB changes this paradigm entirely. It provides a seamless, near real-time analytics solution that eliminates the need for manual ETL. How it works: Analytical Store. When you enable Azure Synapse Link for a Cosmos DB container, Cosmos DB automatically creates a fully isolated, column-oriented analytical store for your data. This analytical store is separate from your transactional, operational store. Automatic synchronization. Changes from your operational store are automatically and near real-time synchronized to the analytical store, without consuming any request units, RUs, from your transactional workload. Azure Synapse Analytics Integration. This analytical store can then be directly queried by Azure Synapse Analytics using different engines. Spark, for big data processing, data science, and machine learning. SQL Serverless Pool, for ad hoc querying with familiar SQL syntax. Benefits: no ETL overhead, dramatically reduces the complexity and cost of traditional ETL pipelines. Near real-time insights. Analysts can query the most up-to-date operational data almost instantly. Zero impact on operational workload. Analytical queries run against the analytical store, ensuring your transactional Cosmos DB database remains performant for its primary function. Cost-effective. You only pay for the storage in the analytical store and for the compute consumed by the Synapse engines, separating analytical costs from operational costs. Practical insight, as requested in planning. Imagine a scenario where a large retailer stores all its customer order data in Azure Cosmos DB operational store for its transactional website. Simultaneously, data scientists and business analysts need to run complex, ad hoc queries on the same data for trend analysis, forecasting, and personalized marketing campaigns. Without Synapse Link, these analytical queries would either consume valuable RUs from the operational store, potentially slowing down the website, or require a separate, delayed ETL process. With Synapse Link, analysts can use Synapse Studio to query the customer order data directly using Spark or SQL, without affecting the website's performance or incurring any additional RU costs on the transactional database. This is a game changer for hybrid transactional analytical processing, HTAP. 11.5 Stream Processing with Azure Stream Analytics for IoT and real-time insights. Azure Stream Analytics is a real-time analytics service for processing fast-moving streams of data. It's often used with IoT scenarios, but applies to any high-volume event stream. How they integrate: Output to Cosmos DB. Stream Analytics jobs can output processed data directly to an Azure Cosmos DB container. This is ideal for ingesting process telemetry, aggregated data, or real-time insights into Cosmos DB for querying by applications. Input from Cosmos DB, less common, usually change feed preferred. While less common due to the efficiency of the change feed, Stream Analytics can technically serve as an input, reading from Cosmos DB for certain scenarios. Common scenarios: IoT telemetry processing. Ingest raw sensor data, e.g., from an Azure Event Hub, filter, aggregate, e.g., average temperature per device per minute, and then store the process data in Cosmos DB. This reduces the data volume and makes it easier for applications to consume. Real-time anomaly detection. Process a stream of events, identify patterns, and write only anomalous events to Cosmos DB for immediate alerting or further investigation. Clickstream analysis. Analyze user behavior on a website in real time and push personalized content decisions or session summaries into Cosmos DB. 11.6. Enhancing search capabilities with Azure Cognitive Search. Azure Cosmos DB is excellent for fetching data based on precise IDS or structured queries. However, it's not a full-text search engine out of the box. For rich, full-text search experiences, e.g., fuzzy matching, faceting, scoring, natural language queries, Azure Cognitive Search, formerly Azure Search, is the dedicated solution. How they integrate? Indexers. Azure Cognitive Search provides a built-in Cosmos DB indexer. This indexer can automatically ingest data from your Cosmos DB container and keep the search index synchronized as changes occur. It leverages the change feed internally. Skill sets. Cognitive Search also allows you to define skill sets to enrich data during indexing, e.g., extract entities, detect language, translate, using AI services. Common scenarios. E-commerce product search. Provide a rich search experience for your product catalog stored in Cosmos DB, allowing users to search by keywords, filter by categories, brand, price range, and sort results, with facets to narrow down options. Document retrieval. Index large document repositories stored in Cosmos DB to enable powerful keyword searches within their content. Knowledge bases. Create searchable knowledge bases based on content in Cosmos DB, with features like synonym mapping or custom scoring. This combination allows you to leverage Cosmos DB for its operational strengths while providing best-in-class search capabilities through cognitive search. 11.7. Building event-driven pipelines with Azure Event Hubs and Service Bus. While Cosmos DB's change feed natively streams changes, sometimes you need more sophisticated messaging capabilities, especially when integrating with systems that aren't direct change feed consumers, or when building complex microservices architectures. Azure Event Hubs, a highly scalable data streaming platform and event ingestion service. Integration. An Azure function or Stream Analytics triggered by the Cosmos DB change feed can push events to Event Hubs. This acts as a central hub for millions of events per second, which can then be processed by various consumers, e.g., real-time dashboards, big data analytics engines, other microservices. Use cases. IoT message ingestion into Cosmos DB, or broadcasting Cosmos DB changes to a wide array of event consumers for real-time processing and big data analytics. Azure Service Bus, a fully managed enterprise integration message broker. Integration. Azure Functions or your application could push messages to Service Bus queues or topics based on Cosmos DB events. Use cases. Orchestrating complex workflows where messages need reliable delivery, transactional processing, or advanced routing patterns, e.g., sending an order fulfillment message, processing payments, dealing with failed transactions with dead letter queues. These services complement the change feed by providing robust, scalable, and reliable messaging infrastructure for your event-driven microservices, enabling your Cosmos DB changes to propagate effectively throughout your application landscape. 11.8. Security and networking. Integrating with Azure VNet and private endpoints. Security is paramount for any production database. Azure Cosmos DB offers robust security features that integrate deeply with Azure's networking capabilities. Virtual Network (VNet) integration. You can configure your Cosmos DB account to only accept connections from within a specific Azure virtual network. This creates a private, isolated network boundary for your database. Benefits: prevents connections from the public internet, reducing the attack surface. Enhances network security and compliance. Azure Private Endpoint. This provides a secure, private connection from your VNet to your Cosmos DB account without requiring public IP addresses. Data travels directly on the Microsoft Backbone network, bypassing the public internet entirely. Benefits: enhanced security, zero data exfiltration risks, simplified network configuration. IP firewall rules. You can configure IP-based firewall rules to limit access to your Cosmos DB account to specific public IP addresses or ranges. While less secure than VNet integration or private endpoints, it's a good first line of defense for non-VNet resources. Role-based access control, RBAC. Azure RBAC allows you to manage who has access to your Cosmos DB resources and what they can do, e.g., read-only, read-write, manage databases containers. Managed identities. For Azure-hosted applications, like Azure Functions, Web Apps, VMS, managed identities eliminate the need for developers to manage credentials, like master keys. Your application simply uses its own Azure AD identity, which is securely managed by Azure, to authenticate with Cosmos DB. This is the most secure and recommended way to connect Azure services to Cosmos DB. These networking and security integrations are critical for building compliant, secure, and robust enterprise-grade applications with Cosmos DB. 11.9 Cost considerations of integrated architectures. Optimizing across services. When building solutions that integrate Cosmos DB with other Azure services, it's crucial to consider the overall cost implications. Each service has its own pricing model, e.g., compute, storage, data egress-ingress, operations. Understand consumption patterns. Analyze how much data is flowing between services, how often functions are triggered, and the compute consumption of your Stream Analytics or Synapse jobs. Optimize each service individually. Apply cost optimization best practices to each service, e.g., for Cosmos DB. Right-size RUS, use autoscale, leverage TTL for functions. Optimize code for cold starts, choose appropriate plan. For Synapse, optimize queries, suspend pools when not in use. Data transfer costs. Be aware of data transfer costs, especially across regions or out of Azure. Services in the same region usually have lower or no data transfer costs. Synapse Link for analytics. If you have significant analytical workloads, enabling Synapse Link is usually far more cost-effective than running complex analytical queries directly against your transactional Cosmos DB data, as it offloads RU consumption and leverages optimized analytical compute. Managed identities versus connection strings. While a security measure, managed identities can indirectly save costs by simplifying credential management, reducing exposure to breaches that might lead to unexpected usage. By taking a holistic view of your architecture's cost, you can make informed decisions about combining services to achieve your performance, scalability, and budget goals. This chapter has demonstrated that Azure Cosmos DB is a foundational component within the Azure cloud, designed to integrate seamlessly with a wide array of other services. By leveraging these integrations, developers can unlock unparalleled power and flexibility, building robust, scalable, and intelligent applications that meet the demands of today's complex digital landscape. Chapter 12. Best Practices, Monitoring, and Troubleshooting for Developers. 12.1 The Path to Production. Beyond development to operational excellence. You've learned the core concepts of Azure Cosmos DB, its distributed nature, data modeling, various APIs, and how to perform fundamental CRUD operations, craft efficient queries, manage consistency, partition your data, and leverage the change feed. You've also seen how it integrates seamlessly with other Azure services to build powerful solutions. However, building an application that works in development is one thing. Deploying and maintaining a robust, performant, and cost-effective solution in production is another. This final chapter consolidates essential best practices for operating Azure Cosmos DB, guides you through effective monitoring, and equips you with troubleshooting techniques to handle common issues that may arise in a production environment. Operational excellence is crucial for unlocking the full potential of your Cosmos DB-powered applications. 12.2 SDK Best Practices: maximizing your application's efficiency and reliability. The Azure Cosmos DB SDKs are the primary interface between your application and your database. Using them effectively is key to application performance and stability. Initialize and use a single client instance, singleton pattern. As discussed in Chapter 4, the Cosmos client, or equivalent in other SDKs, should be initialized once at application startup and reused throughout your application. This optimizes connection pooling, reduces overhead, and improves latency. Avoid creating new client instances for every request. Asynchronous programming, async await. Always use the asynchronous methods provided by the SDK, e.g., createItemAsync, query definition create iterator. This prevents your application threads from blocking while waiting for database operations, improving scalability and responsiveness, especially in web applications or microservices. Handle errors with care, leverage retries. The SDK's built-in automatic retry mechanism for transient errors, like 429 throttling, is invaluable. Your application should focus on handling non-transient errors, e.g., 400 bad request, 404 not found, 409 conflict, gracefully. Configure connection options. Tune connection mode. Direct mode is generally preferred for performance, preferred regions, and timeouts based on your application's deployment environment and network conditions. Project-specific fields. In your select queries, always specify only the fields you need, e.g., select C, id, C.name from C. Rather than selecting all fields, select from C. This reduces network payload and deserialization overhead, saving RUs. Utilize point reads where possible. For single item retrieval by id and partition key, use the dedicated readItemAsync, or equivalent, method. It's the cheapest and fastest operation. Implement optimistic concurrency. Use e-tags, Chapter 5, to prevent lost updates when multiple clients modify the same document simultaneously. Batch operations for atomicity. For operations affecting multiple items within the same logical partition that must succeed or fail together, use transactional batch, Chapter 5, for atomicity and efficiency. Leverage bulk execution for high throughput. For large-scale data ingestion, updates, or deletions, use the bulk support feature of the SDK to maximize throughput and improve RU efficiency. 12.3 Comprehensive Cost Management Strategies. Keeping your Cosmos DB bill in check. Managing request units, RUs, effectively is paramount to controlling your Azure Cosmos DB costs. Remember, RUs are your billing currency. Right-size provision throughput. Monitor actual usage. Use Azure Monitor to understand your peak RU consumption. Auto-scale for variable workloads. This is often the most cost-effective choice for unpredictable traffic, as it scales down during low usage periods. Container level versus database level. Generally, container level throughput offers better isolation and control over performance guarantees for critical collections. Database level is only cost-effective if you have many small containers where the aggregated traffic is stable. Optimize queries and data modeling. Choose an effective partition key. This is the single most impactful factor for both performance and cost. A good partition key leads to efficient single partition operations. Target queries. Always include the partition key in your queries to route them to a single logical partition. Avoid cross-partition queries unless absolutely necessary and monitor their cost. Strategic indexing. Use custom indexing policies to include only necessary paths and exclude large, unqueried fields. This reduces write RUs and storage. Leverage time to live TTL. For transient data, logs, sessions, temporary caches, enable TTL on your containers or individual items. Cosmos DB automatically deletes expired data, reducing storage costs and freeing up RUs that would otherwise be spent on manual deletions. Choose the appropriate consistency model. Weaker consistency models, eventual, consistent prefix, session, generally offer lower RU costs for read operations than strong consistency. Select the weakest model that meets your application's consistency requirements. Compress data, application side. For very large documents with compressible content, consider compressing them in your application before storing them in Cosmos DB. This can reduce RU consumption and storage, but adds computational overhead to your application. Consider Azure Synapse Link for analytics. If your analytical queries contribute significantly to your RU consumption, offload them to Azure Synapse Analytics Link. This completely separates the analytical workload from your transactional RUs, often leading to substantial cost savings for both. Regularly review and downscale. Actively monitor your provisioned throughput and actual usage during non-peak times. Don't be afraid to reduce your RUS during quieter periods if your workload allows. 12.4 Securing your Cosmos DB application. A developer's essential guide. Security must be an integral part of your application's design, not an afterthought. Managed identities recommended. For Azure-hosted applications, Azure Functions, App Services, VMS, always use Azure Managed Identities for authenticating with Cosmos DB. This eliminates the need to store and rotate connection strings or keys, reducing the risk of credentials being compromised. Role-based access control, RBAC. Use Azure RBAC to grant the principle of least privilege. Assign specific roles, e.g., Cosmos DB built-in data contributor, to your managed identities or users, giving them only the permissions they need to perform their tasks and nothing more. Avoid using the master key for application-level access in production. Network isolation with private endpoints and VNets. For enhanced security and data exfiltration protection, enable Azure Private Endpoints for your Cosmos DB account and integrate it with your Azure Virtual Network, VNet. This ensures all traffic to Cosmos DB travels over Microsoft's private backbone network, bypassing the public internet entirely. IP firewall rules. As a strong secondary or complementary measure, configure IP firewall rules to limit access to your Cosmos DB account to only trusted IP addresses or ranges, always encrypted for sensitive data. While Cosmos DB encrypts data at rest and in transit by default, for highly sensitive data where you need to preserve client-side encryption and protect data from accidental exposure even within Cosmos DB's backend, consider using the Always Encrypted feature. This ensures sensitive data remains encrypted end-to-end. Key rotation. If you must use master keys for some reason, e.g., non-Azure hosted applications, establish a regular key rotation policy. Secure API keys. If you expose an API, e.g., via Azure API management, that interacts with Cosmos DB, ensure your API keys, not your Cosmos DB master keys, are securely stored and rotated. 12.5 Monitoring your Cosmos DB solution with Azure Monitor. Gaining visibility and insights. Effective monitoring is crucial for identifying performance issues, detecting anomalies, and troubleshooting problems proactively. Azure Monitor provides comprehensive monitoring capabilities for Azure Cosmos DB. Azure Monitoring Metrics. The Cosmos DB blade in the Azure portal integrates directly with Azure Monitor, providing a rich set of metrics for your account, databases, and containers. Total request units, RUS, your actual consumption versus provisioned throughput. This is the most critical metric for performance and cost. Throttled requests, HTTP 429, indicates that your application is hitting throughput limits. Latency, average and P99 latency for reads and writes, crucial for understanding user experience. Data usage, storage consumption. Normalized RU consumption indicates how close you are to exhausting your provisioned RUs, providing a percentage utilization. Availability, end-to-end availability of your account. Diagnostic logs. Enable diagnostic logging to send detailed operational logs, e.g., data plane requests, resource logs, to a log analytics workspace, storage account, or event hub. These logs are invaluable for granular troubleshooting and security auditing. Log analytics queries. Use Custo query language, KQL, in log analytics to analyze patterns in your logs, identify top consumers, long-running queries, or IP addresses accessing your database. Alerting. Set up alerts in Azure Monitor based on key metrics or log events. High throttling rate. Alert if 429s exceed a threshold. High latency. Alert if P99 latency for reads or write spikes. RU consumption nearing limit. Alert if normalized RU consumption exceeds 70 to 80% of provisioned RUs. Storage exceeding threshold. Alert if data usage approaches a capacity limit. Azure dashboards. Create custom dashboards in Azure Portal to visualize your most critical Cosmos DB metrics at a glance. Anecdote. The case of the spiky bill and the missing index. A development team launched a new feature that allowed users to search historical data. Days later, their Azure bill spiked unexpectedly, and users reported slow search response times, occasionally receiving service unavailable messages. Their monitoring showed a dramatic increase in RU consumption and intermittent 429 errors. By drilling into Azure Monitor metrics, they identified that the spike correlated with high usage of a specific cross-partition query on the historical data container. The query stats in the Data Explorer further revealed that this query was consistently performing full scans and consuming thousands of RUs per execution due to lack of an adequate composite index. They quickly added the necessary composite index, which reduced the query's RU cost to tens of RUs, eliminated the 429s, restored performance, and brought the Azure bill back within budget. This demonstrated the direct linkage between monitoring, understanding RU consumption, and effective indexing. 12.6 Common troubleshooting scenarios and solutions for developers: throttling, latency, data issues. Being able to diagnose issues quickly is crucial. Here are common problems and how to approach them. Throttling, HTTP 429, too many requests. Symptom, operations fail part of the time with 429 errors. Cause, you are exceeding your provisioned throughput, RUS. Troubleshooting, check Azure Monitor. Compare actual RU consumption with provisioned RUS, identify peak times and the query's operations causing the spike. Analyze query RUs. Use Data Explorer or SDK diagnostics to find expensive single queries or operations. Identify hot partitions. Use Azure Monitor's normalized RU consumption by partition key range metric to see if one logical partition is consuming a disproportionate amount of RUs. Solution, increase provisioned throughput. Simplest solution, especially with autoscale. Optimize queries, add update indexes, filter by partition key. Optimize data model. Reevaluate partition key choice if hot partitions are occurring. Leverage bulk execution for write-heavy operations. Implement backoff. Ensure your application uses the SDK's automatic retries and implements proper backoff logic for 429s. High latency. Symptom, operations are slow, application feels unresponsive. Cause, network issues, high RU consumption leading to throttling, inefficient queries, suboptimal client configuration. Troubleshooting. Check Azure Monitor. Look at latency metrics. Is it high for reads, writes, or all operations? SDK diagnostics. Use the diagnostic string available in SDK responses, e.g., diagnostics in net. This provides granular details on network latency, retries, and server-side processing time for each request. Verify connectivity. Is your application in the same Azure region as your Cosmos DB account? Check SDK configuration. Are you using direct mode? Is the client singleton? Are preferred regions configured for global distribution? Solution. Follow throttling solutions if 429s are contributing. Optimize network path, VNet private link. Ensure client-side best practices. Data inconsistencies / unexpected data. Symptom, reads return outdated data or data appears to be intermittently missing or out of order. Cause, misunderstanding or misconfiguring consistency models, external systems not syncing correctly if using change feed. Troubleshooting, verify consistency level. Check the consistency level configured for your Cosmos DB account and for specific operations in your code. Understand guarantees. Revisit Chapter 7. Does the observed behavior align with the chosen consistency model's guarantees? For example, in eventual consistency, reading stale data is expected. Check for lost updates. If multiple clients are writing to the same document, verify that optimistic concurrency control, (ETAGs), is correctly implemented. Change feed issues. If consuming the change feed, ensure your change feed processor is running, not falling behind, and handling idempotency correctly. Solution: adjust consistency level to a stronger one if required. Implement OCC properly. Reevaluate change feed processor reliability. High Azure bill. Symptom: your monthly Cosmos DB bill is much higher than expected. Cause: overprovisioned RUs, inefficient queries, high storage costs for unneeded data, or excessive cross-partition operations. Troubleshooting: use Azure cost management tools. Analyze Cosmos DB costs by resource, identify top consumers. Solution: follow all the strategies in Section 12.3 on cost management. Downscale RUs, optimize queries, leverage TTL, utilize Synapse Link for analytics. 12.7 Performance Tuning Checklist for Developers. Optimizing queries and workloads. Here's a quick checklist to guide your performance tuning efforts. Is your Cosmos client a singleton? Crucial for connection efficiency. Are you using asynchronous operations, async await? Prevents thread blocking. Are you using point reads for single item lookups? Read item async. Is your partition key effectively distributing data and RUs? Check metrics for hot partitions. Are your most frequent queries targeted to a single partition? Query includes partition key in where clause. Are you using custom indexing policies to support your most common queries, especially for order by and multi-property filters? Are you only selecting necessary fields in your queries, not select? Are you using continuation tokens for pagination, not offset limit? Are you considering patch operations for small, targeted updates? 10. Is your throughput, RUS, provisioned correctly and utilizing autoscale for variable loads? 11. Are you enabling TTL for transient data? 12. Is your application handling 429s gracefully using SDK retries? 13. Are you leveraging bulk operations for high-volume ingest updates? 14. For analytical workloads, are you considering Azure Synapse Link? 12.8 Backup, restore, and disaster recovery considerations for business continuity. While Cosmos DB automatically handles data replication for high availability, understanding its backup, restore, and disaster recovery capabilities is essential for robust business continuity planning. Automatic backups. Cosmos DB performs automatic, continuous backups of your data. These backups are taken without impacting performance, stored in Azure storage, and are geo-redundant within their region. Continuous backup with point-in-time restore. This advanced feature, currently for core SQL API, allows you to restore your data to any point in time within the last 30 days. It creates a continuous stream of backups, enabling very granular recovery options in case of accidental deletions or corruption. This is the recommended backup solution for business-critical workloads. Periodic backups. The older, default backup policy is periodic, taking snapshots every 4 hours and retaining the last 2 backups. For more granular recovery, continuous backup is superior. Data replication for disaster recovery, geo-redundancy. Beyond backups, Cosmos DB allows you to add multiple replica regions to your account. This ensures that your data is replicated globally. In the event of a regional outage, Cosmos DB can fail over to a healthy replica region, maintaining high availability for your application. This is separate from backups and focuses on active-active or active-passive high availability. You can configure manual or automatic failover. Recovery Point Objective (RPO) and Recovery Time Objective (RTO). Understand your application's RPO, how much data loss is acceptable, and RTO, how quickly your application needs to be back online. These define your disaster recovery strategy and influence your choice of consistency model, backup policy, and multi-region setup. 12.9 Continuous improvement. Staying up to date with Cosmos DB updates and features. The Azure Cosmos DB team continually releases new features, performance improvements, and SDK updates. As a developer, it's crucial to stay informed. Microsoft documentation. The official Azure Cosmos DB documentation is comprehensive and always up to date. Azure blog and release notes. Follow the Azure blog and Cosmos DB release notes for announcements of new features and capabilities. SDK updates. Regularly update your SDKs to the latest stable versions to benefit from performance improvements, bug fixes, and new features. 12.10 Looking ahead. The future of Azure Cosmos DB for developers. Azure Cosmos DB is a foundational service in Microsoft's cloud strategy, constantly evolving to meet the demands of modern applications. As you continue your journey, expect further advancements in expanded serverless capabilities, more features, and possibly higher limits for the effortless, consumption-based model. AI and machine learning integration. Tighter integration with Azure ML and other AI services for real-time inference and data enrichment. Developer experience. Continued improvements in SDKs, tooling, and integration with popular developer frameworks. Performance and cost optimizations. Ongoing enhancements to the underlying engine to deliver even lower latency, higher throughput, and better cost efficiency. You are now equipped with the knowledge and best practices to design, develop, deploy, and manage highly scalable, globally distributed applications with Azure Cosmos DB. Embrace the iterative nature of cloud development, continuously monitor, optimize, and leverage the vast Azure ecosystem to build truly remarkable solutions. Happy coding!